Hello there, and welcome to our channel. The little corner where curiosity settles in, the questions slow down, and science takes its time instead of rushing past in a blur. Tonight, or whatever moment you've arrived in, we're wandering into one of the quiet mysteries hidden in the long memory of our planet. It's a mystery that doesn't shout, doesn't happen suddenly like a storm front, and doesn't follow the same schedule as the seasons we're used to. It's something that creeps in over tens of thousands of years, happening so slowly that no one has ever watched it begin or end in real time. And yet, it's shaped the world in ways far more dramatic than most of us realize. We're talking about the strange rhythm by which Earth freezes over and then warms up again, over and over, every 100,000 years or so. Not because the planet is indecisive, but because it's following patterns written into its orbit, its tilt, and its own internal systems. Before we drift deeper into that story, I'd love to know where you're listening from tonight, or this morning, or whatever moment your own clock says you're in. Maybe it's late and you're winding down. Maybe it's early and the day hasn't quite started yet. Wherever you are, whenever you are, this is one of those topics that connects all of us across time zones because it reaches far beyond the span of human history. If you find this kind of slow, steady exploration calming or interesting, or just a good way to unwind, I'd be very grateful if you gave the video a like, or maybe subscribed. It helps this quiet space find others who might need a moment of ease too. Now let's ease into the question. Earth doesn't freeze randomly. It doesn't slip into icy ages because of a sudden event or a single cause. There's a pattern to it. Subtle at first glance, but unmistakable once you know where to look. Imagine for a moment that the entire history of civilization is only a sliver on a much bigger timeline. A fraction of the cycles the planet has gone through. We've built cities, created stories, invented tools, and mapped continents. All during a period of unusual stability, one of the rare warm intervals between long frozen expansions. Human beings appeared, grew, traveled, settled, and built everything we recognize today. Not during an age of ice, but during what scientists sometimes call an interglacial, a warmer pause between enormous advances of ice sheets that once reached far into regions that now feel temperate and familiar. This warm pause we're living in right now is temporary, at least on geological timescales. It's a brief sigh in a pattern much longer than any human story. And understanding why the freeze comes at all requires looking at Earth, not just as a place we walk on, but as a world that moves in ways we rarely think about. It tilts, it wobbles, it shifts its orbit. These motions are so slow that they pass unnoticed within a lifetime. But over very long spans, they accumulate, nudging the climate into new shapes. The cold doesn't arrive all at once. It gathers slowly. One winter, slightly longer. One summer, slightly cooler. Ice lingering a little more stubbornly. Year after year, until the planet finds itself locked into a new mood entirely. The question isn't just why Earth gets cold, but why it does so with such a rhythm. About every 100,000 years, the ice sheets expand in a sweeping movement that can remake coastlines, shift habitats, and reshape continents. And then, just as slowly, they retreat. These are changes so vast that if we could watch them unfold on fast forward, the continents themselves would seem to breathe, exhaling ice outward and drawing it back again in long, measured cycles. The tricky part is that Earth doesn't have just one factor that controls its climate on these scales. It's more like a collection of mechanisms that all influence each other. They push and pull, reinforce, and sometimes resist, creating a pattern that's consistent but not perfectly symmetrical. And every part of that pattern has a role in deciding when ice grows and when it melts. The starting point for this long rhythm lies in the way Earth moves around the Sun. The planet's orbit isn't a perfect circle, and its tilt isn't fixed. Over tens of thousands of years, these slow shifts alter how sunlight reaches the planet's surface. Not the total amount, but the distribution. Northern summers can become slightly cooler, southern summers slightly warmer, or the opposite, depending on the cycle. These slight changes add up. A cool enough summer means snow doesn't melt completely. When snow lingers, it reflects more sunlight. When it reflects more sunlight, temperatures inch downward again. Over centuries and millennia, this feedback grows stronger. What begins as a subtle change becomes a driver of ice, expanding sheet by sheet. Even with that, Earth doesn't freeze on schedule like a clock. The cycles influence the climate, but the climate also has a sort of momentum. Oceans move heat around with slow, deep currents. Ice stores cold in vast, gleaming expanses that take ages to form or melt. Greenhouse gases rise and fall as natural systems breathe in and out. All these factors give Earth layers of timing. When they align just right, ice surges forward. When they fall out of sync, warmth returns. And for reasons scientists continue to study, those alignments hit a strong rhythm roughly every 100,000 years. You might imagine all of this as the planet's slow pulse, one that doesn't match human expectations because it isn't based on anything we directly feel. Our familiar seasons come and go in predictable cycles. Winters start, end, and return in patterns we understand easily. But geological seasons unfold so slowly that you'd never notice the beginning or the end in a lifetime. The early signs of an ice age are almost impossible to detect without scientific tools. It starts with summers just slightly cooler than the ones before. Year after year, snow lingering a little longer, ice building a little thicker, plants shifting their growing regions, animals altering their behavior, their migrations, their habitats. Eventually, after thousands of years, everything has shifted far enough that a new world has emerged without a single dramatic moment marking its arrival. What makes this rhythm even more intriguing is how dependent it is on regions that don't seem especially central at first glance. Large ice sheets form primarily in the far north because that's where sunlight can vary enough to matter. A slight change in summer warmth in those high latitudes can change how much snow remains year after year. And once that ice is established, it expands outward, cooling the climate beyond the areas where it originally formed. The South matters too, but the Northern Hemisphere has more land at high latitudes, so ice can build more effectively there. Oceans respond slowly but decisively, changing the way they circulate heat. Air patterns shift, dust levels rise. Everything from plant cover to atmospheric gases begins adjusting to the new conditions. As strange as this may seem, this cooling and warming cycle has been happening for millions of years. Forests have grown and retreated. Grasslands have spread and shrunk. Rivers have changed their courses. Species have adapted, moved, or vanished. During the last major freeze, enormous ice sheets covered regions that today hold cities, farmland, and roads. Much of northern Europe, Canada, and parts of Asia were buried under layers of ice thick enough to flatten mountains. The sea level dropped dramatically, exposing land bridges that connected continents. Ancient humans migrated across these new paths, following animals or escaping cold in ways that shaped our own evolutionary story. When the warmth eventually returned, it didn't sweep away the ice in a dramatic rush. It was just the opposite. A millimeter here, a centimeter there. Small changes building slowly as centuries passed. Ice shrank so gradually that no one alive at the time could have noticed anything more than typical seasonal patterns. But over long spans, the land rebounded, coastlines shifted, rivers carved new paths, lakes formed in basins left by retreating ice. Ecosystems reorganized themselves into new communities. All of this happened while early human societies were still hunter-gatherers, adapting to their surroundings, without knowing the larger forces at work. What's remarkable is how consistent this overall pattern has been in recent geological history. Not perfectly consistent, but steady enough that scientists can track each cycle through evidence buried in ocean sediments, ice cores, and layers of rock. These natural archives record changes in temperature, atmospheric composition, and the extent of ice. They show periods of long freezes and shorter warm intervals, all in a repeating rhythm, driven by the planet's own motions. And yet, there's a twist. Something changed about 1,000,000 years ago. Before that, the cycles were shorter, around 40,000 years each. Then, for reasons still being studied, Earth slipped into a new rhythm, stretching the cycles to 100,000 years. It's one of the puzzles at the heart of paleoclimate science, and every new discovery adds another layer to the investigation. Understanding these long cycles isn't just about explaining the past. It's also about understanding how sensitive Earth's climate is to small changes in sunlight and feedback loops. If slight shifts in orbit or tilt can trigger ice ages, then the balance of heat and cold is more delicate than it might appear. Every part of the system, from greenhouse gases to ocean circulation to ice albedo feedbacks, plays a role. And these interactions don't move quickly. They roll forward like slow waves, gathering momentum over centuries. Despite how dramatic ice ages seem in retrospect, the early stages unfold softly. There's no single moment when you could say, "This is the start." It's more like watching a very slow sunrise or sunset, where the light shifts so gradually that only when you look back do you see how different things have become. And that's part of what makes this story so absorbing. It's not the tale of sudden events, but of slow, steady forces quietly shaping the world beneath our feet. Everything we experience today, from the coastline shapes to the ecosystems around us, carries subtle marks of these cycles. The soil under forests, the shape of valleys, the movement of rivers, the distribution of species, the presence of lakes that once filled meltwater basins, even the minerals carried by winds. All of these have been touched by the advance and retreat of ice. Our world is a product of frozen ages we never witnessed, but live with every day. And as we continue, we'll move gradually through the forces that control this long freeze and thaw pattern, exploring how slight changes in Earth's movement can shift entire ages, and how the planet itself reinforces or counteracts those changes. There's a quiet logic to it, one that unfolds slowly, but once you see the pieces, the rhythm becomes unmistakable. And with that, let's drift a little deeper into the story of how these long climate patterns form and why they follow such steady cycles. taking our time as the planet does. When seasons stretch into ages, it becomes necessary to shift the way we think about weather. Not as something that changes week to week or month to month, but as something that unfolds so slowly it can't be felt within a human lifetime. The familiar seasons we're used to, the ones that mark our calendars and signal when to plant, when to harvest, when to bring out warm clothes or open windows, are only surface patterns compared to the much longer climate patterns that shape the Earth over tens of thousands of years. These long patterns are not just extended winters and summers. They're changes in the entire system. Shifts in the balance between sunlight, land, and atmosphere that slowly nudge the planet toward colder or warmer conditions. When trying to understand deep time weather, it helps to imagine the planet as a system that always wants to stay in balance. It absorbs energy from the sun and releases energy back into space. If the amount absorbed and the amount lost are equal, the climate stays stable. If something changes the balance, even by a small amount, the climate begins to shift. In the span of a year or a decade, this kind of shift doesn't amount to much. But in the span of thousands of years, it builds into something large enough to expand ice sheets or melt them away. The sort of weather we're talking about in these long cycles isn't the type that changes daily or even yearly. It's better to think of it as a gentle but relentless push. One summer is slightly cooler than the last. One winter holds its snow a little longer. One patch of ice reflects a bit more sunlight than it did a century before. Nothing dramatic is happening at any one moment, but the accumulation becomes impossible to ignore once it reaches a tipping point. If you could lay thousands of years side by side like photographs in a long album, you'd see the slow drift from warmth into cold, from mild summers into ones that never quite melt the winter's snowfall. Most of us think about weather in short bursts because that's how we live. We check forecasts, compare one season to the next, and sometimes wonder why a particular year is warmer or colder. But deep time, weather doesn't care about these short intervals. It depends on cycles far larger than human experience. If you were to stand in the same place for 100,000 years, the changes would look like a slow sweep, as though the seasons were stretching themselves longer and longer until they became something entirely different. The first step in understanding this scale is recognizing that Earth's climate is influenced by more than just the sun's brightness or the gases in the atmosphere. Those matter, of course, but in deep time, the biggest influences come from the way Earth moves through space. That movement determines how much sunlight different parts of the planet receive and when they receive it. Even tiny variations in that sunlight spread across thousands of years can reshape entire continents. This isn't easy to picture because the changes are so small, year to year. Imagine the difference between a summer that is 1 degree cooler than average. In a single year, that doesn't feel like much. You'd still have warm days, plants would still grow, and the snow would still melt. But if every summer for thousands of years is just slightly cooler, the snow might not melt completely. It might linger, compact, and turn into ice. The next year adds a little more. A century later, a significant patch of ice covers the land. 10 centuries later, it becomes a sheet. After thousands of years, it grows into a massive ice cap. This is how seasons stretch into ages. It's not a sudden shift, not a world waking up one morning to find itself in an ice age. It's a long accumulation of small, steady changes. And these changes don't happen everywhere at the same time. One region may cool first. Another may resist the change for thousands of years. Some regions might even warm slightly while others cool. But as the balance of energy changes across the planet, the overall direction becomes clear. Ice grows in places where summers can't melt the snowfall. Water evaporates less readily. Glaciers spread slowly. Wildlife and vegetation move in response to the creeping cold. To understand why this happens, it helps to look at the forces that push the climate over such long time scales. Earth's orbit changes, shaped slowly over tens of thousands of years. Its tilt shifts gradually. Its axis wobbles in a slow circular motion. All of these motions change how sunlight reaches the planet and which regions get the most or least solar energy during summer. These are not dramatic changes. They don't alter the total sunlight reaching Earth. Instead, they change the distribution. When summers become slightly weaker in northern latitudes, ice can grow. When summers strengthen, ice melts. The northern hemisphere plays a central role in these long climate patterns because it contains the largest land areas at high latitudes. Ice builds more effectively on land than on ocean because snow can accumulate in layers without spreading out or melting from below. Land also absorbs heat differently than water, responds more quickly to cooling or warming, and allows ice to stay in place. These land masses, especially in areas like Canada, Northern Europe, and Siberia, act like shelves where snow can pile up year after year until the cold becomes self-reinforcing. When snow reflects sunlight, cooling increases. When cooling increases, more snow stays frozen. When more snow freezes, even more sunlight is reflected. This process continues until an entire region transforms into a cold zone where ice dominates. These regions then influence the entire planet. The atmosphere responds to the ice cover. Winds shift. Storm tracks change. Oceans circulate differently. Animals and plants migrate or adapt. Deep time weather is the combined effect of all these responses, accumulating over spans of time far longer than any human memory. To get a sense of the pace of these changes, imagine the climate as a slow-moving river rather than a rapid stream. It doesn't twist suddenly. Instead, it gradually adjusts its course over immense distances. The temperature of the planet drifts very slowly until it reaches a point where ice can grow or shrink significantly. This drift is not something anyone living through it would notice day to day. No one would say the climate changed dramatically this year. But if someone could compare two snapshots thousands of years apart, the difference would be unmistakable. What's truly interesting about deep time weather is how interconnected everything becomes. A slight shift in sunlight patterns affects the polar regions. Those regions then affect ocean temperatures. Ocean temperatures affect the way heat moves around the planet. The distribution of heat affects winds. Winds affect moisture patterns. Moisture patterns affect vegetation. Vegetation affects how much sunlight is absorbed. And all of these feedbacks return to influence the climate again, creating a loop where the system reinforces its own direction. It's not always a simple loop, though. Sometimes feedbacks push in opposite directions. For example, as ice grows, it cools the air, encouraging more ice to grow. But at the same time, colder air can hold less moisture, limiting snowfall. If less snow falls, ice growth can stall. These competing forces interact constantly, making climate change in deep time a complex balance between reinforcement and limitation. The final result depends on which forces dominate over long intervals. These long timelines also mean that Earth's climate has significant inertia. Once the planet starts cooling into an ice age, it doesn't stop easily. Even if orbital conditions begin shifting toward warmer summers, the existing ice sheets take a long time to melt. They are massive, thick, and capable of creating their own cold environments by reflecting sunlight. In the same way, once Earth begins warming out of an ice age, the ice cannot hold its ground. Its retreat becomes a slow but unstoppable process once certain thresholds are crossed. All of this makes deep time weather feel almost like a separate category of climate entirely. The weather we notice influences our daily decisions. The weather in deep time influences coastlines, ecosystems, and even the rise and fall of species. The slow movement of ice sheets during these long periods has carved valleys, shaped mountains, and left behind deposits of rock and sediment that remain in place long after the ice has disappeared. These marks on the landscape tell the story of climates that no one witnessed, but every living thing has been shaped by. It can feel strange to think that the climate we're so accustomed to is just a momentary pattern in a far larger cycle. The warm interval we live in today is short when measured against the long stretches of cold that dominate Earth's recent geological past. The landscapes we recognize as stable are actually temporary formations in a constantly shifting system. Grasslands have covered areas that are now forests. Forests have grown where tundra once stretched. Lakes have filled basins that were previously dry. The remnants of old climates are embedded in the ground, showing where glaciers once stood and where they receded. Understanding deep time weather means accepting that the Earth is not static. It drifts slowly between states, each lasting far longer than any human civilization. The cycles of freezing and thawing have shaped species, migrations, and entire ecosystems. Every part of the planet carries some memory of these long patterns, whether in the form of glacial deposits, ancient shorelines, or fossilized remains of plants and animals that lived in climates very different from the ones seen today. Earth doesn't move from one climate state to another in straight lines. It doesn't cool evenly or warm evenly. Different regions respond at different rates. Some areas cool faster because of changes in sunlight or altitude. Others warm sooner because of local geological conditions or circulation patterns. This unevenness creates complex mosaics of climate zones during transitions between ice ages and warmer periods. Animals and plants respond by shifting their ranges slowly, following the climates they are adapted to. Some species thrive in cold and expand during ice ages. Others shrink or move toward warmer regions. These migrations take place over thousands of years, leaving behind fossils that help scientists reconstruct how ancient environments changed. One of the most important insights from studying these long-term patterns is that the climate system is sensitive to small changes when measured over long periods. A slight shift in the tilt of the Earth might change summer temperatures by just a fraction of a degree in certain regions. But that fraction accumulated year after year can determine whether snow melts or persists, whether ice retreats or advances. Over long enough time frames, small differences grow into dramatic changes, demonstrating how interconnected and delicate the climate system is when viewed in geological terms. The transformations that happen during these long cycles are not random. They follow a pattern shaped by orbital cycles, feedback mechanisms, and the distribution of continents and oceans. Scientists studying deep time weather look for signatures of these cycles in ice cores taken from Antarctica and Greenland. These cores preserve layers of snow and ice that formed over hundreds of thousands of years, trapping tiny bubbles of ancient air that reveal past temperatures and atmospheric conditions. Ocean sediments contain the remains of microscopic organisms that responded to cold and warm conditions differently, creating patterns that reflect past climates. Together, these pieces of evidence reveal a picture of Earth's climate that moves slowly and steadily between extremes. Warm periods show higher levels of certain greenhouse gases, different ratios of oxygen isotopes, and distinct layers of sediment. Cold periods display lower levels of greenhouse gases, different isotopic signatures, and thicker layers of materials dropped by melting icebergs. Each cycle is unique, shaped by specific combinations of orbital patterns and feedback effects, but the overall rhythm remains consistent. These cycles show that Earth's climate is not accidental. It follows a set of long-term rules that govern when ice builds and when it melts. Recognizing these rules helps explain why Earth experiences such long cold cycles. It also helps explain how sensitive the planet is to changes in sunlight distribution, even if the overall energy coming from the sun remains constant. The patterns we see today are part of a story that has been repeating for millions of years. And understanding this story provides insight into how Earth responds to shifts in its orbit, its tilt, and its own internal systems. There is a small detail about Earth that most people know, but rarely think about in depth. Something so ordinary, it fades into the background of how we understand seasons. Earth leans. It doesn't stand upright as it circles the sun. Instead, it tilts at an angle that seems almost modest when you hear the number, about 23 and 12 degrees. It's one of those facts learned early in school and then quietly carried into adulthood without much reflection. But that subtle tilt, steady yet constantly shifting over long spans of time, is one of the most powerful forces shaping the long climate cycles that lead to ice ages. It determines how sunlight falls across the planet and how intensely the seasons unfold. And over tens of thousands of years, its slow variations drive changes significant enough to transform entire continents. To understand why the tilt matters so much, it helps to picture Earth not as a static globe, but as a spinning body that keeps the same lean as it orbits the sun. Because of this lean, the sun's rays strike different hemispheres with different strength throughout the year. This difference creates the seasons we're familiar with. When the northern hemisphere leans toward the sun, it experiences longer days and warmer temperatures. When it leans away, the opposite happens. This is straightforward when thinking of a single year. But the long-term behavior of Earth's tilt adds another layer that operates on a much slower schedule. The angle doesn't stay fixed at 23.12 degrees. It swings gently between about 22 and 24.102 degrees over a cycle lasting roughly 41,000 years. A shift of just a few degrees might seem mild, especially when the planet continues spinning and orbiting and delivering familiar seasons each year, regardless of the exact tilt. But over long spans of time, these slight differences change how strong summers are in high latitudes. And when examining whether ice can melt or remain, strong or weak, summers are far more important than the temperatures of winter. Snowfall can pile up endlessly each winter, But if summer is warm enough, it melts away and the balance resets. Only when summer is too cool to melt all the snow does ice begin to accumulate over time. This is where Earth's tilt becomes essential. When the tilt is larger, closer to 24°, seasons become more extreme. Summers in high latitudes receive more concentrated sunlight. Winters become darker and colder, but the stronger summers tend to melt whatever snow or ice built up during the winter. Under these conditions, ice sheets struggle to grow. They might still expand a bit during particularly cold intervals, but the general tendency is for melting to keep pace with snowfall. Warmer, high-latitude summers act as a climate brake, preventing ice from advancing too far. When the tilt decreases, moving toward the lower end of its range at around 20°, the opposite happens. Seasons become slightly milder. Winter is still cold in high latitudes, of course, but summer loses some of its intensity. Days are still long in northern regions during summer, but the sun's rays arrive less directly. They carry less energy. They melt less snow. They create conditions where snow and ice can accumulate from one year to the next. This small reduction in summer warmth is one of the key ingredients in triggering the slow build of ice sheets. Over many centuries, the effect compounds. Snow that lingers becomes compacted. Compacted snow hardens into ice. Ice spreads outward, reflecting more sunlight and cooling the region further. The reduced tilt doesn't cause an ice age on its own, but it prepares the stage, setting a background condition where ice can grow if other factors also align. What makes this interesting is how delicate the balance is. A change of just a degree or two in tilt stretched across tens of thousands of years determines whether summers have enough strength to melt winter's accumulation. It's tempting to think of seasons as fixed cycles. But over long durations, even small changes in the amount of sunlight reaching a particular region can shift the climate in ways that reshape the entire planet. The tilt doesn't change abruptly. It moves slowly, taking tens of centuries to crawl from one extreme to the other. No individual generation would ever notice the difference. But if you could compare summers separated by several thousand years, the shift would be obvious. One would show stronger sunlight at high latitudes, melting ice with confidence. The other would show weaker sunlight, allowing snow to remain longer each year and turning the region slightly colder. When trying to imagine how this plays out, consider a region like northern Canada or Scandinavia. Today, their summers are short but warm enough to clear the snow completely. But under a slightly reduced tilt, summers in these places would be less able to melt the snow that accumulates. If even a small portion of snow is left behind each year, the next year adds more, and the next adds more, slowly building a foundation for future ice. You wouldn't notice it across a human lifespan, but the land would begin changing subtly as centuries pass. Forests would retreat. Tundra would expand. Eventually, something that began as slightly cooler summers transforms into a landscape dominated by ice. This gradual change is one of the reasons ice ages don't begin suddenly. They require these long, slow drivers to push the climate in one direction. And the tilt cycle is one of the strongest of those drivers. It determines how much energy high latitudes receive precisely during the season that matters most for melting, snow and ice. Interestingly, winter temperatures have far less influence on the formation of ice sheets. No matter how cold winter becomes, snowfall still melts if summer is warm enough. The key is always the strength of summer sunlight, and that strength rises and falls with the tilt. The tilt cycle interacts with other elements of Earth's long-term climate system. When the tilt is low and summers are weaker, other cycles, such as changes in Earth's orbit and the wobble of its axis, can either reinforce or oppose the cooling effect. When several of these long cycles align in a way that weakens high-latitude summers, ice can begin growing in earnest. When they align to strengthen summer sunlight, ice retreats. These combined effects give the climate its complex rhythm. But the tilt remains one of the clearest signals in how the seasons stretch into long phases of cold or warmth. Another important aspect of the tilt is how it affects sunlight distribution, not only across latitudes, but also across different surfaces. Land responds more dramatically to changes in sunlight than oceans do. Water absorbs heat more slowly and releases it slowly, creating a buffering effect. Land, on the other hand, warms and cools quickly. This means that when Earth's tilt reduces summer sunlight in northern regions, the land areas at high latitudes become especially vulnerable to cooling. They lose heat quickly and gain it slowly, helping snow and ice remain in place. Since the northern hemisphere contains more land at high latitudes than the southern hemisphere, it is more affected by tilt changes. This geographic difference is one of the reasons ice ages grow ice sheets, mainly in the north, even though the tilt affects the entire planet. If Earth had a completely different layout of continents, the effect of tilt changes might look different. But with large land masses positioned in the northern hemisphere, especially in areas like Canada and northern Eurasia, the climate becomes especially sensitive to long-term changes in seasonal sunlight. These regions respond quickly to cooling by building snow and ice. Once that begins, the ice reflects sunlight, reducing warming and encouraging even more cooling. This is why the tilt cycle, while subtle, plays such a central role in driving the major climate cycles of the last few million years. Scientists studying these cycles rely on evidence locked in natural archives to see how the tilt influenced past climates. Ice cores from Greenland and Antarctica showed distinct layers representing different eras, allowing researchers to measure past temperatures, atmospheric conditions, and even the amount of sunlight that reached the surface indirectly through proxies. These cores capture chemical signatures that correspond to warm or cold periods. When compared with known variations in Earth's tilt, the patterns match clearly. Warmer periods correspond to times when tilt was larger, leading to stronger high-latitude summers. Cooler periods correspond to times when tilt was smaller, allowing snow to persist and ice to build. Ocean sediments also hold clues, especially in the shells of microscopic organisms that responded to ocean temperatures differently in warm and cold conditions. Their remains create patterns in the sediment layers that reveal when ice expanded or retreated. What emerges from studying these records is a climate system that responds in predictable ways to long-term changes in tilt. The planet warms or cools depending on how much high-latitude summer sunlight reaches the surface. And this slow shift influences everything else. It changes the amount of water locked in ice sheets, altering sea levels. It shifts wind patterns and ocean currents, redistributing heat. It shapes ecosystems by changing where plants and animals can thrive. Over long intervals, the tilt cycle becomes a kind of metronome for Earth's climate, guiding the rhythm, even when other factors join in the process. The tilt also contributes to transitions between climate states. When the tilt begins increasing, after reaching its minimum, summers grow slowly stronger. For centuries, the effect might be too small to make a noticeable difference. But eventually, the increasing summer sunlight becomes sufficient to melt more snow and ice than accumulates each winter. This doesn't cause an immediate retreat of ice sheets, but it starts the long process. Once melting begins, it accelerates. Ice that has been stable for thousands of years starts shrinking, exposing darker land surfaces that absorb more heat. As heat absorption increases, melting speeds up. Over many millennia, the ice recedes across vast distances. In this way, the tilt doesn't just contribute to the onset of ice ages, but also to their ending. The same mechanism that helps ice grow when summers are weak helps ice melt when summers strengthen. This makes the tilt a kind of pivot point in the climate system. When it moves in one direction, the planet trends toward cold. When it moves in the other, it trends toward warmth. It is not the sole driver, but its influence is strong enough to set the overall direction of climate change in deep time. An interesting part of understanding this tilt cycle is appreciating how slow it really is. A full swing from maximum to minimum tilt takes tens of thousands of years. No one living at any moment could perceive the change directly. Generations would come and go without noticing that sunlight was falling slightly differently than before. Yet over the span of the entire cycle, the accumulated effect is unmistakable. It changes landscapes, coastlines, ecosystems, and even the migration routes of humans and animals. It's a reminder that the forces that shape the planet don't always announce themselves quickly. Some of the most powerful ones operate on timelines far beyond our immediate awareness. Thinking about this slow-moving process also highlights the complexity of the climate system. The tilt doesn't act alone. It becomes part of a larger pattern that includes the shape of Earth's orbit, the wobble of its axis, greenhouse gas concentrations, ocean patterns, and feedback effects involving ice, vegetation, and atmospheric moisture. Each of these components operates on different time scales and with different intensities. But the tilt's contribution remains one of the clearest, and its cycle is one of the more predictable elements of deep-time climate behavior. All of this shows how something as simple as Earth's lean can drive immense changes when viewed across long durations. The tilt is small in angle, but large in influence. It shapes the strength of seasons, the potential for snow to melt, and the foundation for ice sheets to grow. Without this slow variation, Earth's climate would still change from other factors, but the dramatic cycles of ice ages might not look the same. They might be weaker or occur differently. The rhythm of 100,000 years that has dominated recent ice age cycles depends on multiple factors, but the tilt remains one of the key components. Earth's orbit seems at first glance like the most straightforward part of the story. The planet circles the sun, completing its path in a little over 365 days. We learn this early in life, and the idea becomes so familiar that it hardly draws attention. It appears simple, a yearly loop that repeats itself, giving us the seasons, anchoring calendars, and guiding everything from agriculture to school schedules. But the simplicity is only apparent when we think about it on short time scales. Over thousands of years, the orbit is not fixed. It shifts gradually, changing shape and altering how Earth receives sunlight at different times of year. These shifts take place slowly enough that no one would notice them in a lifetime. Yet the accumulated changes have been powerful enough to help trigger the major ice age cycles that occur roughly every 100,000 years. Understanding this long-term orbital behavior requires thinking of Earth's path as something that isn't rigid. It's not a perfect circle. It's not even a constant ellipse. Instead, its shape gently expands and contracts over a cycle lasting around 100,000 years. The orbit shape can vary from being nearly circular to being slightly stretched. The difference might seem minor, but it influences how much sunlight reaches Earth at various points in its journey. This variation, known as eccentricity, is one of the longest and slowest cycles affecting Earth's climate. When the orbit is nearly circular, the distance between Earth and the Sun doesn't change very much throughout the year. One side of the orbit doesn't bring Earth significantly closer or farther from the Sun than another. The seasons are shaped mostly by the planet's tilt, not its distance. But when the orbit becomes more elongated, Earth spends part of the year noticeably close to the Sun, and part of the year noticeably farther. In the present day, Earth's orbit is only slightly eccentric, meaning the difference isn't dramatic. But over thousands of years, the cycling between greater and lesser eccentricity changes how the planet experiences sunlight in subtle but important ways. It can be tempting to think that the planet's distance from the Sun determines whether we enter an ice age. After all, if Earth were farther, temperatures would drop. But the relationship isn't that direct. Even when the orbit becomes more stretched, the planet as a whole receives almost the same total amount of sunlight per year. What changes is how sunlight is distributed across seasons. When Earth's orbit is more elongated, seasonal contrasts can become stronger or weaker, depending on how the orbit aligns with Earth's tilt and its axis. These interactions are complicated, but they influence whether high-latitude summers become strong enough to melt snow or weak enough to let it accumulate. During periods when the orbit is more stretched, one hemisphere might experience stronger seasonal differences depending on whether Earth is closest to the Sun during its summer or its winter. When Earth is closest to the Sun, during Northern Hemisphere winter, for example, winters become milder because the Sun's energy is more intense at that time of year. But summers might also become slightly cooler because Earth is farther from the Sun during that season. It's the reduced strength of Northern Hemisphere summers that opens the door for ice to build, because ice sheets depend much more on summer melting than on winter snowfall. As long as summer temperatures dip slightly, snow remains unmelted and begins the slow transformation into ice. During periods when the orbit is more circular, these differences lessen. Summers and winters rely almost entirely on the tilt for their seasonal behavior. But even then, the background effect of eccentricity still matters because it amplifies or weakens the influence of the other long-term cycles, involving tilt and axial wobble. When eccentricity is large, the combined effects of the orbital cycles become more pronounced. When eccentricity is small, those combined effects become weaker. This is one of the reasons the 100,000-year rhythm stands out so clearly. The eccentricity cycle provides the long-term modulation that strengthens or weakens the impact of the other cycles. When all of them line up in a way that reduces Northern Hemisphere summer warmth, the planet shifts into an ice age. A good way to picture this is to imagine Earth's climate system as a series of overlapping influences, each following its own long schedule. The tilt changes more quickly, over about 41,000 years. The wobble of Earth's axis shifts over roughly 26,000 years. But eccentricity, the shape of the orbit, changes over about 100,000 years. When the orbit becomes more stretched, the effects of tilt and wobble can act more strongly. When the orbit becomes more circular, those effects are muted. It's easy to miss how these cycles work together because on their own, none of them fully explains the pattern of ice ages. But when combined, they form a pattern that aligns with the major advances and retreats of ice sheets seen in geological records. One of the most important consequences of changes in orbital shape is how they influence the amount of summer sunlight at high northern latitudes. The northern hemisphere, with its abundance of land at high latitudes, is especially sensitive to these changes. Land absorbs heat quickly and loses it quickly, making it more responsive to variations in sunlight. The ocean does not behave the same way. Water absorbs heat slowly and releases it slowly, creating a buffer that dampens temperature swings. This difference means that any orbital cycle affecting sunlight will have a greater impact on land-heavy regions. As a result, northern summers become the key indicator of whether an ice age can begin. If summers weaken due to the combined effects of tilt, wobble, and orbital shape, the climate slowly shifts toward conditions that allow snow to persist year after year. Once this process begins, it becomes difficult to reverse until the cycles line up again in a way that strengthens high-latitude summers. Another way eccentricity influences climate is through its relationship with the timing of the seasons. Over long spans, the position of Earth in its orbit during solstices and equinoxes shifts slowly. This means that summer in a given hemisphere might occur when Earth is closer to the Sun during one long cycle and when it is farther during another. This gradual shift is part of the axial wobble cycle. But the eccentricity cycle determines how significant the distance difference is. If the orbit is nearly circular, Earth's position doesn't matter much because the distance barely changes. But if the orbit is stretched, the position becomes crucial. A single season occurring when Earth is closer to the Sun becomes warmer than it would otherwise be. The same season occurring when Earth is farther away becomes cooler. This changes the melting power of summer, which ultimately determines whether ice sheets can grow. The idea that ice ages depend more on summer conditions than winter might seem counterintuitive. People often associate ice ages with colder winters, but the real driver is whether snow melts in summer. Snow can fall heavily in a warm climate, but as long as the summer warmth clears it, no ice accumulates. For ice sheets to grow, snow must persist. Persistent snow becomes ice, and ice becomes a climate force in itself. This is why slight weakening of summer sunlight can initiate a long chain of changes leading to major glaciations. When studying eccentricity's influence on climate, scientists look at evidence preserved in ocean sediments, ice cores, and rock formations. These records show repeating patterns of temperature change, ice volume, and sea level movements. By comparing these patterns with known variations in Earth's orbital shape, researchers see clear correlations. Periods when the orbit was more stretched often correspond to times when ice sheets expanded or retreated, depending on how other cycles aligned. But what stands out most is how eccentricity modulates the climate system. it doesn't control it alone. Instead, it sets the background conditions that allow or inhibit ice growth. It's like adjusting the volume on a system of overlapping signals. When eccentricity increases, the other orbital cycles become more influential. When it decreases, their influence weakens. The slow cycling of eccentricity also interacts with the feedback loops built into Earth's climate system. When ice begins to form due to weaker summers, ice reflects sunlight, cooling the region further. This cooling adds to the effect of the orbital cycles, amplifying their impact. The more ice builds, the more the climate cools. Likewise, when conditions shift toward warming, melting ice exposes darker land or ocean surfaces that absorb more heat. This accelerates warming. Eccentricity acts as the long-term rhythm, guiding how strong these feedbacks can become. One of the most striking aspects of studying these long-term orbital patterns is how small the differences appear when expressed in everyday terms. A change in Earth's orbit that modifies its distance from the Sun by a few percent doesn't sound dramatic, but over long periods, small differences accumulate. The climate system responds slowly but steadily. Snow that lingers year after year creates enormous ice sheets that take ages to build and ages to melt. Coastlines shift as sea levels rise or fall. Ocean currents reorganize themselves as global temperatures change. These are not sudden transformations, but slow, gradual adjustments that only become obvious when viewed across thousands of years. Earth's orbit, changing slowly in shape, does not act like a switch that triggers ice ages instantly. Instead, it sets the conditions under which ice can either accumulate or disappear. When the orbit becomes more stretched and aligns with other long-term cycles that weaken high-latitude summers, the climate drifts toward colder conditions. When the orbit shifts back toward a more circular shape, the influence of those cycles weakens, allowing ice to retreat. The rhythm created by these changes doesn't always follow the exact same timing. Some ice ages last longer than others. Some warm periods extend for shorter or longer intervals. But the overall pattern reflects the slow modulation of Earth's orbit, interacting with the other orbital motions and the climate system's internal feedbacks. The orbit cycle also reveals something important about Earth's climate history. About 1 million years ago, the rhythm of ice ages changed. Before that time, the major cycles occurred every 40,000 years, corresponding more closely to the tilt cycle. After that transition, the dominant rhythm shifted to around 100,000 years, matching the eccentricity cycle. Scientists continue to investigate why this shift occurred. Some suggest that ice sheets grew larger and more stable during this era, making them more responsive to the long eccentricity cycle. Others propose that changes in ocean circulation or greenhouse gas levels altered the climate system sensitivity. What remains clear is that the eccentricity cycle gained prominence, shaping the climate in a new rhythm that continues today. Understanding this long orbital dance also highlights how interconnected Earth systems are. The orbit doesn't change rapidly. Its slow pacing interacts with even slower feedbacks in the oceans, as well as more direct ones involving ice and land. The atmosphere responds to these changes gradually. Vegetation shifts. Water moves into or out of ice sheets. The planet's surface is constantly responding to the interplay between orbital conditions and internal climate mechanisms. No single factor acts alone, but the orbit's slow cycling provides a long foundation upon which the other changes unfold. This shifting orbit doesn't affect the planet evenly. Different regions respond differently depending on latitude, altitude, and proximity to oceans. Some areas feel the effects of weaker summers long before others. As cooling continues, new regions become susceptible to snow accumulation. Ice grows not just in one place, but across multiple regions, once conditions allow. This expansion changes the planet's energy balance further, allowing the cooling to continue. In this way, the slow shift in orbit acts as a quiet but persistent influence that builds gradually until the climate reaches a new state. While the orbit shape changes slowly, the timing of these changes is remarkably consistent when viewed across millions of years. The cycles repeat predictably, allowing scientists to track past ice ages and forecast future ones in broad terms. This doesn't mean the exact timing of future ice ages is simple to calculate, because human activities have altered atmospheric composition significantly. But the underlying rhythm of orbital change remains the same. It continues whether the climate responds immediately or not. The orbit will keep shifting long after our current era. The climate will continue responding in ways that follow the same physical rules as before, just on timescales much longer than those we usually consider. Thinking about this orbital rhythm helps put Earth's current warm period into context. The planet has been in a relatively stable interglacial phase for thousands of years, benefiting from orbital conditions that support stronger northern hemisphere summers and limit ice growth. But these conditions will not last forever. Eventually, orbital cycles will align in ways that weaken summers again. When that happens, if the climate system is still capable of responding in the same way, snow may begin to accumulate more persistently in high latitudes. Ice could begin its slow expansion once more, beginning the next long glacial period. Whether this happens on schedule or is delayed by changes in atmospheric conditions remains an active area of research, but the long-term orbital dance continues regardless. The idea that Earth wobbles might sound like an exaggeration at first, because the word calls to mind something unstable or unsteady. But the wobble in question is neither chaotic nor abrupt. It is a slow, predictable shift in the orientation of Earth's axis, so gradual that it takes nearly 26,000 years to complete one full cycle. This motion, known scientifically as axial precession, is one of the quiet forces operating behind the scenes in the long climate patterns that lead the planet into and out of ice ages. Although the wobble doesn't change the actual tilt of Earth, it changes the direction the tilt is pointing, which alters when seasons occur in Earth's orbit. Over thousands of years, this shifting orientation changes the distribution of sunlight during key parts of the year, shaping the long-term climate in ways that would never be apparent to someone observing it over a lifetime. To understand precession, it helps to imagine Earth as a spinning top. When a top spins quickly, it stands upright, but as it slows down slightly or interacts with external forces, it begins to trace a slow circular motion with its axis. Earth behaves in a similar way, though the time scale is vastly different. Its axis points toward a particular location in the sky, currently close to the star Polaris. But this wasn't always the case, and it won't remain so in the distant future. Thousands of years ago, the axis pointed toward a different star, and thousands of years from now, it will point elsewhere. This slow rotation of the axis changes the orientation of the seasons relative to Earth's position in its orbit. What makes this wobble significant for climate isn't the change in which star marks the pole, though that detail is interesting for navigation and astronomy. Instead, its importance lies in how it rearranges the timing of the seasons. Because Earth's orbit is not perfectly circular, it has points where the planet is closest to the Sun and farthest from it. Today, Earth is closest to the Sun during Northern Hemisphere winter and farthest during Northern Hemisphere summer. But the wobble gradually shifts which season align with these orbital positions. Over thousands of years, winter and summer slowly trade places relative to Earth's distance from the Sun. This subtle rearrangement influences the strength of the seasons, especially at high latitudes, where ice sheets are most sensitive to changes in summer warmth. When Northern Hemisphere summer occurs, while Earth is closer to the Sun, summers become somewhat warmer. This additional warmth makes it harder for snow and ice to persist. When summer occurs while Earth is farther from the Sun, summers become cooler, making it easier for snow to linger. In this way, precession can either promote or hinder the growth of ice sheets, depending on how the wobble aligns the seasons with Earth's orbital position. The effect is not dramatic on its own, but combined with the tilt and eccentricity cycles, it contributes to the long-term pattern that determines whether the climate will trend toward warmth or cold. An important part of understanding precession is recognizing that it affects the hemispheres differently. Because the orientation of Earth's axis shifts, one hemisphere will experience stronger seasonal contrasts, while the other experiences weaker contrasts. For example, if Northern Hemisphere summer occurs when Earth is closer to the Sun, summers there are warmer and winters are cooler. But at the same time, the Southern Hemisphere experiences the opposite pattern. Its summer occurs when Earth is farther from the Sun, meaning cooler summers and milder winters. This hemisphere-to-hemisphere trade-off means that precession creates alternating periods, where one hemisphere becomes more favorable for the growth of ice sheets. Of the two hemispheres, the Northern Hemisphere plays a more decisive role in ice age cycles because it contains large land masses at high latitudes where snow can accumulate. The Southern Hemisphere has more ocean at these latitudes, and oceans resist temperature changes more effectively. Because ice sheets grow more readily on land than on water, the sensitivity of northern summers to precession becomes one of the key factors influencing whether an ice age can begin. When the wobble aligns Northern Hemisphere summers with the point in Earth's orbit farthest from the Sun, cooler summers become more common. This creates conditions where annual snowfall can persist and accumulate. When this alignment combines with the tilt cycle in a phase that weakens summer sunlight even further, the stage is set for long-term cooling. Precession not only shifts the timing of seasons, but also alters the distribution of sunlight across different times of the year. This distribution matters because the climate system responds not to yearly averages, but to the strength of sunlight during crucial months, especially during the peak of summer in high latitudes. If the peak summer months receive less sunlight over thousands of years, even by a small margin, the landscape gradually cools. Snow begins to survive longer into the year. Ice forms earlier in winter and melts later in summer. Over many generations, these small shifts accumulate into large changes, eventually creating the foundation for growing ice sheets. One way to picture this is to think of northern summers as the gatekeepers of ice ages. If the gate remains open, meaning summers stay warm enough to clear away winter snow, ice sheets struggle to grow. But if the gate closes, meaning summers weaken enough to let snow persist, ice can build year after year. Precession influences how wide that gate opens each summer by altering the timing of Earth's distance from the Sun. When the wobble positions Earth farther from the Sun during northern summers, the seasons shift into a pattern where the gate slowly closes. Snow lingers, ice forms, the landscape cools further. If precession then aligns with other orbital cycles that also weaken sunlight, the gate closes a bit more. Over thousands of years, it remains shut long enough for an ice sheet to take root and expand. A slow rearrangement of the sky might seem disconnected from the conditions on land, but climate responds to small differences that persist for long spans. Precession changes the intensity of sunlight by amounts that don't matter much from year to year, but matter significantly when averaged across tens of thousands of years. As a result, this slow wobble becomes a key component in the planet's shifting climates. Evidence of precession influence can be found in natural records preserved in sediments, ice cores, and geological formations. Ocean sediments, in particular, provide a clear signal of precession cycles because the shells of microscopic organisms record temperature changes over tens of thousands of years. These organisms respond sensitively to seasonal conditions, leaving behind chemical signatures that reflect past ocean temperatures. When scientists analyze these sediments, they often find repeating patterns that line up with the 26,000-year cycle of axial precession. These patterns reveal alternating periods of warmer and cooler summers in different hemispheres, supporting the idea that precession influences long-term climate behavior. Ice cores also reflect the rhythm of precession. The trapped layers of ice, which contain ancient air bubbles and chemical traces, show variations in climate corresponding to the shifting orientation of Earth's axis. When combined with records of tilt and orbital eccentricity, these ice cores form one of the clearest pictures of how the planet has moved in and out of ice ages. The timing of colder and warmer intervals often align with phases of the precession cycle that weaken or strengthen high-latitude summers. This alignment isn't perfect because other factors influence the climate as well, but the correlation is strong enough to demonstrate precession's importance. One of the subtle but important consequences of precession is its role in determining when ice ages begin and when they end. Precession can create conditions favorable for ice growth, but it cannot sustain an ice age alone. When precession shifts into a phase that strengthens northern summers, ice begins to melt. However, melting does not happen quickly. Ice sheets have enormous thermal inertia, meaning they respond slowly to warming. Even if precession aligns summers with closer approaches to the sun, the existing ice needs millennia to melt back. Only when precession's warming influence combines with changes in tilt and orbit, as well as internal feedbacks like rising greenhouse gas levels, does an ice age end. In this way, precession acts as both an initiator and a contributor. It tilts the balance toward conditions that favor ice growth or retreat, but it does so slowly and subtly. Other factors determine how quickly the climate shifts. Precession is like a gentle push on a massive system, setting the direction of change but not determining the exact pace. The wobble also interacts with Earth's rotation in ways that influence the atmosphere and oceans. As the axis shifts, the distribution of solar heating across the planet changes over long periods. This affects wind patterns, monsoon systems, and ocean currents. While these changes are not dramatic from one century to the next, their gradual buildup contributes to shifts in regional climates. For example, monsoon systems might weaken or strengthen, depending on how precession influences seasonal heating patterns. These regional changes can affect vegetation, water availability, and even the distribution of animal populations over thousands of years. Over very long periods, precession also influences the position of the equinoxes and solstices relative to Earth's orbit. This slow shift, called the precession of the equinoxes, is why the constellations associated with different times of year change slowly as millennia pass. It also means that cultural and historical interpretations of the sky would look very different if viewed from a distant past or far future. But while the astronomical effects of precession are interesting from a historical perspective, its climate effects remain central to understanding Earth's long glacial cycles. When precession is combined with the other orbital cycles, the result is a complex but predictable pattern that appears clearly in geological records. These records show alternating periods where the climate trended toward cooling or warming, depending on how the cycles aligned. Precession influence is most pronounced when eccentricity, the shape of Earth's orbit, is large. During periods when the orbit is more stretched, the distance differences between Earth and the Sun are more significant, increasing the impact of precession. When the orbit is more circular, precession still operates, but its influence is weaker because the seasonal distance differences become smaller. This modulation explains why precession plays a stronger role during some parts of Earth's climate history than others. Because precession operates on a shorter time scale than the tilt or eccentricity cycles, it introduces more frequent shifts in climate conditions. These shifts do not create ice ages on their own, but create variations within broader climate phases. For example, during a glacial period, precession might cause small oscillations in the extent of ice sheets as northern summers weaken or strengthen. During a warm, interglacial period, precession might contribute to fluctuations in temperature or rainfall patterns. These oscillations appear in climate records as repeating pulses that add texture to the broader climate trends driven by the longer cycles. Precession helps shape the climate by changing not only which hemisphere experiences strong or weak seasons, but also the balance between mid-latitude and high-latitude climate patterns. Middle latitude climates can shift in response to changes in the timing of seasonal sunlight, affecting the growth of forests, grasslands, and other ecosystems. Over thousands of years, these shifts influence soil development, the distribution of species, and the shape of landscapes. This interplay between precession and local climates is one of the reasons the planet's ecosystems have moved so significantly over geological time. Although precession is a slow process, the accumulated changes in climate it drives are substantial. The shifting of seasonal timing affects not only temperature patterns, but also precipitation patterns. In some regions, precession influences when rainy seasons occur, shaping river systems and water availability. This long-term variation in climate conditions affects the development of natural environments, leaving signatures in pollen grains sediments, and even the distribution of ancient lakes. These signatures provide scientists with additional evidence of precession's long-term effects. Precession does not change the total amount of sunlight Earth receives each year. Instead, it redistributes the sunlight across seasons. This redistribution might sound minor, but it influences the climate system because certain seasons are more important than others for maintaining or melting ice. As a result, the climate responds more strongly to changes in summer sunlight than to yearly averages. The subtle shifts in summer sunlight introduced by precession become amplified over long periods through feedback loops, such as the interaction between ice and sunlight, changes in vegetation cover, and shifts in atmospheric and oceanic circulation patterns. When examining precession's role in the long freeze cycles of the past million years, it becomes clear that the climate system is highly sensitive to small but persistent changes in seasonal sunlight. The wobble of Earth's axis creates these changes steadily and predictably. The long-term climate shifts resulting from this wobble demonstrate how interconnected the planet systems are. Ice responds to sunlight. The atmosphere responds to ice. The ocean responds to both. Vegetation responds to temperature and precipitation. Each system feeds into the others, amplifying or reducing the effects of precession, depending on the state of the climate at any given time. In this larger picture of long-term climate cycles, precession plays a role that becomes clearer when combined with the tilt and orbital shape cycles. It alters when seasons occur, relative to Earth's distance from the Sun, influencing the strength of sunlight during key parts of the year. It affects hemispheres differently. It creates oscillations within longer climate phases, and over thousands of years, it guides the direction of climate change by shifting the balance of summer warmth. This slow wobble, imperceptible on human timescales, is one of the reasons Earth experiences recurring cycles of glaciation and warming. It helps determine when ice sheets can begin to grow and when they begin to recede. It shapes the climate in ways that are only visible when looking back across many thousands of years. When thinking about why Earth cools enough to grow enormous ice sheets every 100,000 years or so, it might seem natural to imagine that the sun itself must dim or brighten over time. After all, sunlight is the planet's main source of energy. If Earth repeatedly slips into long frozen intervals, perhaps the sun's output changes in cycles as well. But the sun remains remarkably stable over these timescales. It doesn't dim in any way that could drive ice ages. Instead, what changes is how sunlight reaches different parts of Earth at different times of the year. The total amount of sunlight arriving at the planet remains almost constant, but the way it is distributed shifts due to Earth's tilt, wobble, and orbit. These shifts, although small on a yearly scale, accumulate across thousands of years, leading to changes profound enough to cool continents, expand ice, and reshape the climate. This idea that sunlight can fade for certain regions or seasons without the sun itself doming is one of the most essential parts of understanding how ice ages arise. It is not about receiving less energy overall. It is about receiving less energy at the time and place where that energy matters most for preventing snow from accumulating year after year. When Northern Hemisphere summers gradually weaken due to changes in Earth's orbit and axis orientation, sunlight effectively fades in the places that determine whether the planet trends toward warmth or cold. This fading is not a reduction in brightness, but a redistribution. It's the difference between a strong summer sun capable of melting the winter's snow completely, and a slightly weaker summer sun that leaves behind pockets of snow that persist, accumulate, and eventually build into ice sheets. The fading of sunlight is best understood as a seasonal effect. Even a small decrease in sunlight during northern summer can have an outsized impact on the climate, because summer is the season responsible for clearing away the winter snowfall. If summer fails to melt enough snow, that leftover snow forms a foundation for future accumulation. The next winter adds more. The next summer melts a bit less, and the cycle continues. Over long periods, these small changes create thick layers of ice that grow outward and downward, cooling the land and air around them. This behavior is why long-term climate cycles depend far more on summer conditions than on winter conditions. Winters can be brutally cold, but unless summer warmth returns the surface to a snow-free state, the cold persists and compounds. To picture how sunlight can fade for a region without the sun itself dimming, imagine adjusting a lamp in a room. The lamp emits the same brightness, but if you shift it slightly farther away, or tilt it so that its light falls at a lower angle across a surface, the illumination becomes less direct and slightly weaker. Nothing about the lamp has changed, but the effect on the surface is noticeable. Earth experiences something similar when its orbital cycles change the angle at which sunlight strikes high-latitude regions during summer. The sun is just as strong as ever, but its rays arrive with a bit less focus. Over thousands of years, this subtle difference changes the climate. The tilt of the planet, the shape of its orbit, and the direction the axis points all determine how sunlight falls across different latitudes. When these cycles align in ways that weaken sunlight in high-latitude summers, the effect is cumulative. A cooler summer one year has almost no impact, but a cooler summer every year, for thousands of years, gradually pushes the climate toward conditions where ice can grow. This long buildup is almost invisible within human experience because the pace is too slow to detect from one generation to the next. But in geological time, it becomes a force powerful enough to reshape continents. One way to think about the fading of summer sunlight is to consider how differently the sun strikes Earth depending on latitude. Near the equator, sunlight arrives almost directly overhead throughout the year, delivering intense heat. At higher latitudes, sunlight comes at a lower angle, spreading its energy over a larger area and losing intensity as it passes through more of the atmosphere. This geometric effect means that small changes in the angle of the sun's rays can significantly alter how much energy high-latitude regions receive during summer. When Earth's tilt decreases slightly, or when the orbit shifts so that northern summer occurs, while the planet is farther from the sun, the sunlight that reaches northern regions becomes less concentrated. It is physically the same sunlight, but the angle and distance dilute its strength. This diluted sunlight is not enough to melt as much snow. Even a small reduction in melting has consequences. In high-latitude regions, snow and ice reflect sunlight very effectively. When more snow survives summer, a larger portion of the surface becomes reflective. This reduces the amount of heat absorbed by the ground, reinforcing the cooling effect. The more reflective the surface becomes, the less heat it absorbs, creating a feedback loop that makes summers weaker still. Over time, this feedback amplifies the orbital cycles that initiated the cooling, allowing ice sheets to grow beyond what the orbital changes alone could accomplish. The weakening of sunlight in high-latitude summers is not just about angle and distance. It's also about timing. Because Earth's orbit is elliptical, the planet moves faster in some parts of its orbit and slower in others. When the northern hemisphere experiences summer at the farthest point from the sun, the planet moves more slowly along its orbital path. This means summer lasts slightly longer, but the sunlight received during this extended summer is weaker. The cooling effect accumulates day by day, year after year. The slight weakening, though imperceptible in any given decade, reshapes the climate in the long term. The fading sunlight that drives ice ages does not affect the entire planet equally. It is concentrated in the regions where ice sheets can form, primarily in the northern hemisphere. The southern hemisphere has its own climate patterns influenced by precession and orbital cycles as well, but its geography limits the growth of massive ice sheets. The Antarctic ice sheet is already large and stable, and the southern oceans moderate temperature changes. In contrast, the northern hemisphere contains large expanses of land at high latitudes: Canada, Scandinavia, Siberia, where snow can accumulate and persist. This difference makes the fading of northern sunlight especially important for the growth of ice ages. When sunlight weakens in northern summers, forests retreat gradually. Grasslands expand. Tundra spreads into areas previously dominated by trees. Rivers shift their courses as melting patterns change. Wildlife moves accordingly, tracking the climates that suit their needs. These changes do not occur suddenly. They unfold across millennia as ecosystems slowly adjust to cooler temperatures and altered precipitation patterns. What begins as a small reduction in sunlight becomes, through the climate's interconnected systems, a widespread transformation of the landscape. Another aspect of fading sunlight is how it affects moisture patterns. Cooler summers mean less evaporation, which can reduce rainfall in some regions. But in others, the weakening of summer warmth encourages snow rather than rain during transitional seasons. This shift increases the amount of snow available to accumulate during winter, reinforcing ice growth. Over long periods, the balance between rainfall and snowfall changes the moisture stored in ice sheets, rivers, and oceans. This redistribution of water influences sea levels, which fall as ice sheets grow and rise as they melt. The rising and falling of sea levels reshape coastlines and alter habitats for both marine and terrestrial life. Earth's climate system responds to these gradual changes with a layered complexity because every part of the system interacts with others. Ocean currents, for example, shift in response to cooling conditions. Cooler water becomes denser and sinks, influencing deep currents that move heat around the globe. Changes in these currents can either amplify or dampen the cooling trend depending on the pattern. In the North Atlantic, for example, changes in ocean circulation during cooling periods can reduce the transfer of heat from the tropics to higher latitudes, reinforcing cooling. This interplay shows how fading sunlight initiates changes that the climate system then carries forward through multiple pathways over long time scales. Fade in sunlight in northern summers is one of the clearest indicators of when Earth may transition into an ice age. Geological records show that major ice advances tend to begin when orbital cycles align in ways that reduce high-latitude summer sunlight. These records include data from ice cores, ocean sediments, and the distribution of ancient shorelines, all of which show patterns consistent with the idea that weak summer sunlight plays a central role in triggering ice growth. The changes in sunlight distribution do not need to be large. What matters is their persistence. This persistence highlights the long memory of the climate system. Earth doesn't simply respond to current conditions. It responds to the accumulation of conditions over thousands of years. Snow and ice are particularly effective at recording this memory. Once ice sheets begin to form, they take on a life of their own. Their reflective surfaces cool the air around them, making future summers even weaker. Their sheer mass affects atmospheric circulation. Their growth influences ocean levels, currents, and precipitation patterns. All of these effects reinforce the initial cooling caused by the redistribution of sunlight. The fading of sunlight is not uniform across latitudes. Mid-latitude regions also experience changes, but the effects are subtler. These regions might see changes in seasonal timing, growing season length, or temperature extremes over thousands of years. These shifts influence the types of vegetation that occupy these areas. Forests may retreat or advance depending on how the climate evolves. Grasslands may expand or contract. The ecosystems respond steadily to long-term changes in sunlight distribution, even if the local temperature difference seems small from one century to the next. One of the more surprising aspects of fading sunlight is that it works in both directions. When orbital cycles shift in ways that strengthen northern hemisphere summer sunlight, the opposite process unfolds. Snow melts more completely. Ice sheets begin to thin. More land becomes exposed, absorbing more heat. The climate warms gradually. Oceans expand as the water warms and ice melts. Sea levels rise. The feedback loops that once amplified cooling now amplify warming. But just as cooling takes many thousands of years to establish, so does warming. The climate system does not reverse its state quickly. It requires centuries of incremental change before the shift becomes noticeable in geological records. What makes the fading of sunlight such a central piece in the story of ice ages is how consistently it appears in every major glacial cycle of the past million years. Each cycle shows a period when summer sunlight weakens, followed by a slow buildup of ice. Each cycle shows a period when summer sunlight strengthens, followed by a long retreat of ice. The orbit and axis cycles change the timing and intensity of sunlight, and the climate system amplifies those changes through feedbacks involving ice, vegetation, oceans, and the atmosphere. The result is a repeating pattern that reflects the combined influence of orbital mechanics and Earth's internal climate processes. The weakening of sunlight in key regions reminds us that Earth's climate is sensitive not just to total energy, but to where and when that energy arrives. A small shift in timing or distribution can over thousands of years reshape the climate profoundly. These long-term patterns show how the planet responds to subtle but persistent influences, gradually adjusting its systems in ways that are invisible in the short term, but transformative in the long term. When ice begins to form in high-latitude regions, it doesn't simply accumulate like an ever-growing stack of frozen layers. It becomes part of a system that actively shapes its own future. Snow that lingers past the warmth of summer triggers a sequence of changes that make the environment even more favorable for further snow retention. This is one of the reasons ice ages, once they begin, tend to build momentum, slowly but steadily, transforming continents over thousands of years. The growth of ice is not only a reaction to cooler temperatures, it is a driver of additional cooling. It amplifies the initial shift in sunlight distribution and moves the climate progressively toward conditions from which it becomes increasingly difficult to reverse direction. To understand how this works, it helps to start with the snow itself. Snow is one of the most reflective, natural surfaces on Earth. When sunlight strikes fresh snow, most of the energy bounces back into space, rather than being absorbed by the surface. The more snow there is, the more sunlight is reflected. And the more sunlight reflected, the colder the surface becomes. This sets up a positive feedback loop. Slightly cooler summers leave behind small patches of snow. Those patches reflect more sunlight. The surrounding air cools. Next year's snow melts less thoroughly. The patch grows larger. Over many years, snow begins to transition into firn, a dense, compacted, granular snow, and eventually into glacial ice. Once ice forms, it continues reflecting sunlight even more effectively than fresh snow in many situations. The cycle strengthens itself as layers build. This process, often described as ice albedo feedback, is one of the most important mechanisms behind the persistence and expansion of ice sheets. But the term alone doesn't capture how profoundly this feedback shapes climate. It doesn't just cool the immediate area where snow is accumulated. It influences regional temperatures, shifting the patterns of wind and precipitation. As ice sheets grow, they create more opportunities for snow to persist because the surface beneath them remains cold year-round. Ice sheets act as enormous cold reservoirs. They absorb little heat. They release little heat. They maintain a climate that encourages their own survival. This expanding cold surface affects the atmosphere as well. Air that passes over an ice-covered region loses heat quickly, becoming denser and heavier. This cooler, denser air sinks, altering the local pressure systems. These changes can redirect storm tracks, guiding moisture in new directions. Some regions may begin to receive more snow, further encouraging ice to grow. Other regions may become drier, reducing snowfall but still supporting ice because low temperatures prevent melting. The atmosphere's response to growing ice sheets shows how even a local accumulation of snow can ripple outward, affecting larger areas over long periods. Another consequence of expanding ice is its effect on wind patterns. Because temperature differences drive winds, the contrast between cold, ice-covered regions and warmer nearby regions can intensify certain wind systems. These winds help transport moisture and influence where snow falls. In some cases, stronger winds can carry cold air farther south than before, cooling regions that were previously warmer. This gradual reshaping of atmospheric circulation patterns contributes to the overall cooling trend, reinforcing the expansion of ice. As the surface cools, the boundary between snow-covered and snow-free areas shifts. Regions that were once hospitable to forests or grasslands may become too cold for the vegetation to survive. Trees retreat southward, replaced by tundra or bare ground. Vegetation loss can further reinforce cooling because many types of vegetation absorb more sunlight than snow or ice. When vegetation shrinks, less sunlight is absorbed and more is reflected or scattered. This supports the continued expansion of cold conditions, creating another layer of feedback that works alongside ice bow effects. The growth of ice also affects how moisture moves through the atmosphere. Cold air cannot hold as much moisture as warm air. As the planet cools, global humidity levels decrease. This reduces the amount of water vapor in the atmosphere, which lowers the greenhouse effect slightly. Water vapor is a strong greenhouse gas, and even small reductions in atmospheric moisture can lead to subtle cooling. These changes don't cause dramatic temperature shifts on their own, but when added to the effects of expanding ice, they contribute to the slow descent into colder climate phases. Changes in moisture levels also affect snowfall. In some regions, less atmospheric moisture means less snowfall. In others, shifts in storm tracks concentrate snowfall more efficiently in cold, high-latitude zones, where it contributes to ice sheet growth. The distribution of snowfall becomes more uneven. But the areas that matter most for ice accumulation, those with the right combination of temperature, altitude, and geography, can continue receiving enough snow to maintain and expand ice sheets, even if global snowfall declines. The oceans also respond to the growth of ice. As more water becomes trapped in ice sheets, sea levels drop. Lower sea levels expose continental shelves, creating new land areas. These exposed areas reflect sunlight differently than ocean surfaces, contributing to cooling if they are covered by light-colored sediment or seasonal snow. Additionally, changes in sea level alter the shape of coastlines and the patterns of ocean currents. In some cases, newly exposed land can block or route currents that previously delivered warm water to certain regions. This affects the distribution of heat in the ocean and can reinforce cooling in high-latitude areas. The growth of ice sheets also influences how deep ocean water forms. In cold regions, seawater becomes denser as it cools. If ice sheets grow and temperatures drop, regions that produce dense sinking water shift or strengthen, altering global circulation patterns. These deep currents carry cold water across great distances and influence temperatures far from the ice sheets themselves. The interaction between ice growth and ocean circulation is complex, but over thousands of years, ocean patterns adjust to support the cooling trend, initiated by fading sunlight and amplified by growing ice. As ice sheets expand, they also physically reshape the land beneath them. Their tremendous weight compresses the ground, pushing it downward. This process, known as glacial isostasy, alters local elevations and can change how water drains across the landscape. When ice sheets retreat, the land slowly rises again, but this rebound takes thousands of years. The shifting of land under the weight of ice affects rivers, lakes, and groundwater systems. It changes how moisture moves across the land, which can influence the formation of new ice or the stability of existing ice. Though this may seem like a small effect compared to the climate feedbacks, it contributes to the long-term shaping of glaciated regions. A growing ice sheet becomes a climate force in its own right because of its size. Large ice sheets affect atmospheric circulation on continental scales. They can act as barriers that redirect winds and storm systems. When an ice sheet grows high enough, its surface interacts with the jet stream, forcing the upper-level winds to shift around its cold dome. This can create persistent weather patterns that reinforce cold conditions in surrounding regions. The jet stream may become more variable or take on new shapes as it adjusts to the large ice masses. These changes, though slow, contribute to the stability of ice sheets once they reach a certain size. One of the most important steps in the growth of ice sheets occurs when the ice reaches altitudes where temperatures remain below freezing year-round. At high altitudes, temperatures can remain cool enough to preserve ice even when lower elevations see mild summers. As ice thickens, it lifts itself into colder atmospheric layers. This elevation-driven cooling ensures that the upper layers of ice remain frozen and stable. The elevation feedback is another self-sustaining mechanism. The thicker the ice becomes, the higher it rises. The higher it rises, the colder it becomes. And the colder it becomes, the more resistant it is to melting. This elevation feedback is especially important because it makes ice sheets resilient once they reach a certain size. Even if orbital cycles shift slightly toward warmer summer conditions, the height of the ice keeps its upper layers frozen. Only long-lasting changes in sunlight distribution, combined with sustained warming from other factors, can overcome this resilience and begin the long melting process. Another way ice shapes its own future is through its effect on the composition of the atmosphere. As ice expands, certain biogeochemical processes slow down or shift. Vegetation retreats, reducing the uptake of carbon dioxide by plants. Cold oceans absorb more carbon dioxide, lowering atmospheric levels of this greenhouse gas. Even small changes in carbon dioxide levels influence global temperatures. And over thousands of years, these changes reinforce cooling. This feedback adds to the long-term trend toward deep glacial conditions once ice has begun to take hold. Dust also plays a role in the feedback loops that shape ice growth. During cold, dry periods, winds can carry more dust from exposed land surfaces. Some of this dust settles on snow and ice, while dust-covered snow can absorb slightly more sunlight. The increased dust in the atmosphere can also reflect sunlight before it reaches the surface. The net effect varies depending on where the dust accumulates, but in many cases, the overall cooling effect of increased atmospheric dust outweighs the localized warming on ice surfaces. Dust also affects ocean chemistry when it settles on the water, influencing biological activity that in turn affects carbon dioxide levels. All of these feedbacks, snow albedo, atmospheric moisture, vegetation shifts, ocean circulation changes, sea level adjustments, glacial elevation, and changes in greenhouse gas levels, act together across long time scales. They reinforce one another in complex ways, making the growth of ice sheets a slow but powerful process. And none of these mechanisms alone would produce the dramatic glaciation seen in Earth's history, but together they create a climate system where small initial changes, triggered by shifts in sunlight distribution from orbital cycles, grow into large transformations. The remarkable part of this process is how consistent it has been. For the past million years, ice sheets have advanced and retreated in repeating cycles, each beginning with small shifts in sunlight distribution and each amplified by these feedback loops. Geological records show that once ice sheets begin to grow, they tend to continue growing until a significant shift in sunlight during northern summers begins to reverse the trend. The feedback loops remain active until enough warmth returns to overcome the stability of the ice sheets. And even then, the melting process is slow. Understanding how ice builds its own future helps explain why Earth's climate changes in long intervals rather than short ones. Ice sheets do not respond quickly to small shifts. They require thousands of years to grow or shrink. Their size and stability give the climate system a kind of inertia, holding Earth within cold phases or warm phases until multiple factors align to shift conditions. This inertia ensures that ice ages are long-lasting and that warm, interglacial periods, like the one we live in today, are temporary pauses rather than permanent states. The air around us looks empty at first glance, yet it contains elements that influence Earth's climate in powerful ways. Among these elements, carbon dioxide operates with a quiet persistence that becomes especially important over long time scales. It doesn't trigger ice ages on its own, and it doesn't follow a strict, repeating cycle like the orbital patterns that shift sunlight, but it responds to the cooling and warming initiated by those orbital cycles. And in doing so, it reinforces the direction the climate is already moving. Carbon dioxide acts like the breath of the planet, rising and falling as OCE absorb or release it, as vegetation expands or contracts, and as ice sheets alter the environment around them. Over hundreds of thousands of years, these changes form another essential layer of the rhythm that brings Earth in and out of frozen states. To understand how carbon dioxide shapes these long-term cycles, it helps to focus on how the gas behaves when the planet cools or warms. Carbon dioxide traps heat. Even small variations in its concentration influence how much heat escapes into space. A slight drop in carbon dioxide leads to a slight cooling. A slight rise leads to a slight warming. On short time scales, these effects may be subtle, but on long time scales, they add up. When Earth begins cooling because high-latitude summer sunlight weakens, carbon dioxide responds in ways that strengthen the cooling. And when Earth begins warming because sunlight strengthens again, carbon dioxide shifts in ways that support the warming. It doesn't initiate the long cycles, but it amplifies them, making ice ages colder and warm eras warmer. The behavior of carbon dioxide over long time scales is closely tied to the oceans. The ocean holds far more carbon dioxide than the atmosphere. When the surface of the ocean cools, it absorbs more carbon dioxide from the air. Colder water can hold more dissolved gas. As carbon dioxide moves from the atmosphere into the atmosphere contains less of it, lowering the greenhouse effect and encouraging further cooling. This process doesn't happen quickly. It takes centuries for the ocean to absorb or release large amounts of carbon dioxide. But over thousands of years, as ocean temperatures gradually drop during the early stages of an ice age, more and more carbon dioxide moves from the air into the water, reinforcing the cooling pattern. As ice begins to expand, additional factors influence how carbon dioxide shifts. Vegetation cover changes as forests retreat and grasslands or tundra spread into areas that used to be warmer. Plants absorb carbon dioxide for growth, but their ability to store it depends on the climate. In cold periods, especially as ice sheets grow, vegetation can decline in some regions, reducing the amount of carbon dioxide absorbed on land. This effect can partially offset the ocean's absorption, but the ocean plays a much larger role. Its capacity to store carbon dioxide dwarfs the storage capacity of terrestrial ecosystems. As long as the ocean continues cooling, it will continue to draw down atmospheric carbon dioxide, pushing the climate further toward cold conditions. The ocean doesn't just absorb carbon dioxide directly from the air. It also interacts with carbon through biological processes. Microscopic organisms in the ocean use carbon during their life cycles and produce shells made of calcium carbonate. When these organisms die, their shells sink to the seafloor. Over long periods, this movement of carbon from the surface waters to the deep ocean removes carbon dioxide from the atmosphere indirectly. The rate of this biological activity depends on ocean nutrients, temperature, and circulation patterns. During cold periods, changes in wind strength, upwelling, and nutrient availability can increase the efficiency of this biological pump, encouraging more carbon to be stored in the deep ocean rather than the atmosphere. Another factor in long-term carbon dioxide changes is the presence of large ice sheets. As ice sheets grow, they cover vast areas of land that previously supported forests and soils. These ecosystems store carbon in plant biomass and soil organic matter. When ice advances, it wipes out these carbon reservoirs. Some of the carbon stored in soils may be released into the atmosphere over time, but the loss of vegetation reduces the amount of carbon dioxide the land can absorb each year. Meanwhile, colder climates slow the decomposition of organic matter, allowing carbon to accumulate in soils in regions not covered by ice. These changes don't push the climate in one clear direction, but they modify the carbon balance and add to the complexity of the long-term cycles. Carbon dioxide also interacts with dust, which becomes more abundant during glacial climates. Colder periods tend to be windier and drier, exposing land surfaces and allowing fine particles to be carried by the wind. When dust settles on the ocean, it delivers iron and other nutrients to regions that were previously nutrient poor. This can stimulate the growth of microscopic organisms that absorb carbon dioxide, enhancing the biological pump and drawing even more carbon into the deep ocean. The increased carbon uptake reinforces the cooling trend initiated by changes in sunlight distribution and ice growth. As Earth moves deeper into an ice age, carbon dioxide levels tend to drop gradually. These declines are visible in ice core records, which preserve bubbles of ancient air trapped in layers of ice. By analyzing these bubbles, scientists can determine past concentrations of carbon dioxide. The data show that during glacial periods, atmospheric carbon dioxide levels are significantly lower than during interglacial periods. The difference is not enormous when expressed numerically, but its effect on global temperature is substantial when combined with the other cooling factors in place. When the climate begins to warm again, carbon dioxide responds in the opposite direction. As high-latitude summer sunlight strengthens due to orbital cycles, ice sheets begin to melt. This melting exposes darker land and ocean surfaces that absorb more heat. As temperatures rise, the oceans warm and release some of the carbon dioxide they previously absorbed. Warmer water holds less dissolved carbon dioxide, so the gas moves back into the atmosphere. This increases the greenhouse effect, reinforcing the warming. The process, once again, is slow. But as the climate system slowly shifts from a glacial phase toward a warm interglacial phase, carbon dioxide amplifies the emerging trend. Vegetation also returns as ice retreats. Forests expand into areas previously covered by ice or tundra. These forests take up carbon dioxide from the atmosphere, storing some of it in plant biomass. However, the overall effect on atmospheric carbon dioxide during warming periods is dominated by the warming of the ocean and the release of gas back into the air. The expansion of vegetation helps moderate carbon dioxide levels, but it does not overpower the ocean's influence. One of the interesting aspects of carbon dioxide's role in long-term climate cycles is that it acts more like a follower than a leader. It doesn't begin the change. Instead, it strengthens and sustains the direction the climate is already moving. When sunlight fades and ice begins to grow, carbon dioxide decreases and helps the planet cool further. When sunlight strengthens and ice begins to melt, carbon dioxide increases and supports the warming. This behavior makes carbon dioxide a reactive but powerful player in the long cycles of glaciation and delaciation. Even though carbon dioxide responds to changes initiated by orbital cycles, its effect on the climate is not secondary or trivial. It determines how sharply the climate responds to sunlight changes. Without carbon dioxide responding in this way, ice ages would be less intense. The temperature differences between glacial and interglacial periods would be smaller. The growth and retreat of ice sheets would still occur, but the transformations would be less dramatic. Carbon dioxide provides the climate system with an additional form of memory, storing the influence of slow ocean processes and biological activity, and releasing that influence back into the atmosphere gradually. Carbon dioxide's contribution to glacial climates also interacts with other greenhouse gases. Methane, for example, responds to changes in wetlands and biological activity. It tends to decrease during glacial periods when large wetland areas shrink and temperatures drop. Lower methane levels contribute modestly to cooling. Nitrous oxide also varies with climate, though its effects are smaller than those of carbon dioxide and methane. Together, these gases create a background set of conditions that amplify the long-term cooling during glacial periods and the long-term warming during interglacial periods. Because carbon dioxide has such a significant effect on long-term climate, it leaves a clear signature in geological records. Ice cores show repeating patterns of rising and falling carbon dioxide levels that align closely with glacial and interglacial cycles. Ocean sediments reveal changes in the chemical composition of deep waters that correspond to shifts in carbon storage. These patterns help confirm the relationship between carbon dioxide and Earth's long freeze and thaw rhythm. They also help scientists understand how the carbon cycle responds to external forces, whether those forces are orbital variations, volcanic activity, or changes in biological productivity. Another important feature of carbon dioxide's behavior is its slow response time. It doesn't adjust immediately when temperatures change. The ocean takes centuries to mix surface water with deeper layers. Biological processes respond to shifts in temperature and nutrient availability gradually. Soil carbon turnover depends on long-term changes in vegetation and decomposition. These slow response times mean that carbon dioxide does not fluctuate wildly. Instead, it moves steadily in one direction for thousands of years before gradually reversing its trend. This steadiness helps stabilize the long-term climate cycles, making glacial and interglacial phases more coherent and predictable. Carbon dioxide also influences the threshold between climates. The climate system, with all its feedback loops, can be sensitive to small differences in greenhouse gas levels when those differences persist for long periods. Carbon dioxide helps determine how quickly the climate shifts toward a glacial or interglacial phase once orbital conditions begin pushing it in one direction. If carbon dioxide levels drop in response to early cooling, the climate can transition into a deeper glacial state. If carbon dioxide levels rise in response to early warming, the climate can move more quickly toward an interglacial state. These interactions help shape the complex timing of the long cycles. As ice retreats during warming periods, carbon dioxide begins to increase more rapidly. This acceleration occurs because of multiple overlapping processes. Warmer oceans release more gas, vegetation grows and changes its carbon storage patterns. Dust levels decline as the climate becomes wetter, reducing the ocean's iron supply and weakening the biological pump. These changes shift the carbon balance in ways that amplify the warming trend. Eventually, the ice retreats enough to reveal vast areas of land that absorb heat readily, helping the interglacial period stabilize. The atmosphere, oceans, and land interact to produce a relatively warm, stable climate that lasts thousands of years until orbital cycles once again shift sunlight distribution toward weaker summers in the high latitudes. The entire system acts like a slow-moving breath. Carbon dioxide rises and falls in long intervals following the planet's cooling and warming motions. These fluctuations reflect the combined influence of ocean temperature, biological activity, vegetation shifts, and ice sheet growth. Each change in carbon dioxide concentration contributes to a pattern where ice ages deepen gradually and warm periods rise slowly before eventually giving way to the next cycle. What makes carbon dioxide especially important for Earth's long-term climate story is that it bridges the processes happening at the surface with those happening deep in the ocean and within the biosphere. The gas moves between these components in a slow exchange that ensures the climate's direction is reinforced for thousands of years. It responds to the changing temperature of the planet, but it also shapes that temperature in return. The oceans are often described as Earth's great reservoirs of water, but over long spans of time, they function as something else as well. They act as timekeepers. Their currents hold patterns that repeat, shift, and settle across thousands of years. Their depths store the signatures of past climates, keeping records long after the atmosphere and surface conditions have changed. And their vast capacity to move heat from one part of the planet to another helps determine whether Earth leans toward warmth or cold. When thinking about the long cycles that bring on ice ages every 100,000 years or so, the oceans may not seem like the first place to look, but they are central to understanding how the climate responds to the subtle shifts in sunlight that begin the cooling process. To understand the ocean's role in these long cycles, it helps to approach them as a system with a remarkable amount of inertia. The atmosphere can warm or cool quickly. Snow cover can expand or shrink in a matter of years. Vegetation can respond within decades or centuries. But the oceans take far longer to change. Their enormous volume means that even slight adjustments in temperature require centuries or millennia to spread through their full depth. This slow response creates what scientists call thermal inertia. The ocean resists rapid change, absorbing heat or releasing it only gradually. Because of this, the ocean not only moderates the pace of climate change, but also stores the memory of previous climate conditions. One of the most important ways the oceans influence long-term climate cycles is through the movement of heat. Ocean currents distribute heat from the equator toward the poles and from the surface into deeper layers. This circulation acts like a global conveyor, transporting warm water to regions that would otherwise be much colder and carrying cool water to regions that would otherwise be warmer. The strength and pathways of these currents depend on differences in temperature and salinity. When the climate begins to cool, due to weakened summer sunlight in high latitudes, The oceans adjust slowly, changing the way heat is moved across the planet. A key part of this circulation involves the formation of dense sinking water in high-latitude regions. When seawater cools, it becomes denser and sinks, drawing warmer water from lower latitudes to replace it. This process is crucial for transporting heat northward. But as northern regions cool more intensely due to changes in sunlight, the patterns of sinking water begin to shift. If surface waters become fresher from increased snowfall or from melting in the early stages of cooling, their density can change. This affects how water sinks and how deep ocean currents move. These changes may weaken or redirect the flow of heat toward the poles, reinforcing the cooling trend initiated by orbital cycles. Because the ocean normally delivers significant warmth to high-latitude regions, especially in the North Atlantic, any reduction in this heat transport can accelerate the conditions needed for ice sheets to grow. Slightly cooler summers caused by shifts in sunlight distribution already encourage snow to linger. If the oceans begin delivering less warmth at the same time, the cooling becomes more robust. Snow that may have melted in a warmer, oceanic regime could now survive the summer, providing the start of the long feedback loops that produce ice sheets. Over long intervals, ocean circulation patterns can change dramatically. During glacial periods, evidence suggests that deep ocean circulation slows and shifts southward. Water that sinks near Antarctica and the North Atlantic behaves differently from how it does in the interglacial periods. This creates large regions of the deep ocean where cold carbon-rye water remains isolated for thousands of years. These changes in deep circulation influence how carbon is stored and released, shaping the atmospheric carbon dioxide levels that amplify cooling or warming. The oceans, by adjusting their internal flows, become active participants in the glacial rhythm. Another way the oceans shape the long chill is by controlling how much heat escapes back into the atmosphere. When surface waters cool, the layer between warm surface water and cold, deep water becomes less sharply defined. This allows heat to move more easily from the surface to the deep ocean, where it can be stored for long periods. Conversely, during warm periods, a sharper temperature gradient forms between the upper and lower layers, trapping heat near the surface and preventing it from sinking. These shifts in heat storage contribute to the slow transitions between cold and warm climate phases. The oceans also influence climate through their effect on sea level. As ice sheets grow, they lock away vast quantities of water that would otherwise be in the ocean. This lowers global sea level, sometimes by more than 100 m. Lower sea levels expose continental shelves and alter the shape of coastlines. These changes affect ocean currents by creating new pathways or blocking old ones. For example, shallow seaways may close when sea levels drop, cutting off connections between ocean basins. These closures redirect currents and change how heat and salt move around the globe. When sea levels rise again during warming phases, these pathways reopen, contributing to shifts in circulation. These long-term adjustments in sea level create feedbacks that work in step with the cooling process. If ocean pathways that normally carry warm water northward become restricted, less heat reaches high-latitude regions. Snow and ice accumulate more easily. If ocean basins expand or constrict due to sea level changes, they influence how currents mix and where deep water forms. The interactions between sea level, land shape, and currents contribute to the slow, but persistent changes that determine whether Earth enters or exits an ice age. As powerful as horizontal currents are, the vertical movements within the ocean are equally important. Warm surface waters cool as they move northward, become denser, and sink. This sinking motion drives the global conveyor belt. But as ice ages progress, the sinking patterns shift. Some regions that once produced dense sinking water may cool so much that the surface freezes frequently, preventing the formation of dense water. Other regions may become the primary sources of deep water formation. These changes in vertical motion influence how nutrients and carbon move through the ocean. When deep water circulation slows, carbon can accumulate in the deep ocean, lowering atmospheric carbon dioxide levels and reinforcing cooling. The oceans also store another type of memory: chemical signatures. The chemical composition of seawater carries information about past temperatures, biological productivity, and carbon cycling. For example, the ratio of different forms of oxygen in seawater changes with temperature. Shell-building organisms incorporate these oxygen isotopes into their shells. When these organisms die and sink to the seafloor, their shells become part of the sediment. Over time, these layers record a detailed history of ocean temperatures. By analyzing these sediments, scientists can reconstruct past climates and identify the timing of glacial and interglacial cycles. The sediments also record changes in deep ocean circulation. The distribution of certain chemicals, such as carbon isotopes, shows how water moved through different ocean basins in the past. During glacial periods, deep ocean waters often become more stratified, meaning the layers do not mix as much. This stratification traps carbon in the deep ocean. During interglacial periods, mixing increases, releasing more carbon back into the atmosphere. These patterns closely match the timing of carbon dioxide rises and falls in ice records, reflecting the close link between ocean processes and atmospheric composition. Because the oceans respond so slowly, they act as a stabilizing force in the climate system. They prevent rapid swings in temperature and help the planet transition gradually between glacial and interglacial states. But this stability also makes it difficult for the climate to reverse direction. Once the oceans have settled into a particular mode, when the oceans store large amounts of carbon and heat in their depths during glacial periods, it takes thousands of years of warming to release that carbon and heat back into the atmosphere. This slow release reinforces the long duration of warm interglacial phases once they start. One of the more subtle roles the ocean plays in the long chill involves currents near the equator. These currents distribute heat differently, depending on wind patterns and temperature gradients. During glacial periods, wind patterns shift due to the contrast between cold polar regions and warmer equatorial regions. These shifts influence how warm water spreads across the tropics and how heat is transported poleward. Even though these changes may seem small compared to the large movements of the major ocean currents, they contribute to the overall balance of heat in the climate system. Another important oceanic influence involves the formation and melting of sea ice. Although sea ice is not as thick or long-lasting as the massive ice sheets on land, it plays a crucial role in regulating how much heat the ocean releases into the atmosphere. When sea ice forms, it insulates the ocean surface, reducing heat loss from the water to the air. This keeps cold conditions in place. When sea ice melts, the dark ocean surface absorbs more heat, contributing to warming. The expansion and contraction of sea ice follow seasonal cycles, but also respond to the broader cooling or warming trend of the climate over thousands of years. These long-term changes in sea ice extent modify how much heat the oceans retain or release, supporting the larger climate shifts driven by orbital cycles. The memory stored in the oceans is not only about temperature and carbon, but also about time. The deep oceans circulate so slowly that some water masses remain isolated for hundreds or even thousands of years. These deep waters carry chemical signatures from the surface conditions at the time they sank. When they eventually rise again, they bring clues about past climates to the surface. This slow cycling of water links different eras of the planet's climate system, making the ocean both a transporter and a historian. In thinking about the oceans as timekeepers, it becomes clear how deeply they shape the pace of Earth's long freeze cycles. They determine how quickly the climate can shift, how long cold or warm periods last, and how the climate responds to the initial push from orbital changes. Without the ocean's slow response and long memory, the swings between glacial and interglacial climates would look very different. The transitions might be more abrupt, and the peaks of cold or warmth less stable. But the oceans introduce a kind of long-term moderation, ensuring that changes unfold gradually and with a coherence that spans tens of thousands of years. These oceanic processes also help explain why Earth's climate has such a distinctive rhythm during the past million years. Before this period, glacial cycles were shorter, lasting around 40,000 years. Then about 1,000,000 years ago, the rhythm shifted to the longer 100,000-year cycles we see today. Many scientists believe that changes in ocean circulation, combined with the growth of larger ice sheets and the strengthening of feedback mechanisms, contributed to this shift. The oceans, by altering their capacity to store heat and carbon, may have helped establish the longer cycles that now dominate Earth's climate system. The complexity of ocean behavior also reminds us that climate does not change because of a single factor acting alone. It changes because multiple systems interact over long intervals, each reinforcing or moderating the others. The oceans do not cause ice ages by themselves, but they support and sustain the conditions that allow ice ages to grow deep or to end slowly. They connect the atmosphere, land, and ice in a cycle that loops repeatedly over geological time. For most of the past few million years, Earth followed a rhythm that looked quite different from the one we know today. The cycles of freezing and thawing were shorter, lasting around 40,000 years each. They followed a pattern shaped largely by the tilt of the planet, which changes over that same period. These cycles were regular and recognizable, leaving clear signatures in the geological record. Then, about 1,000,000 years ago, something changed. The rhythm shifted. Ice ages began lasting much longer. Instead of growing and retreating every 40,000 years, ice sheets started expanding and shrinking on a 100,000-year cycle. This shift remains one of the central mysteries in the study of Earth's long-term climate. The orbital cycles themselves did not change during this transition. The tilt still cycles over 41,000 years. The wobble still cycles over 26,000 years. The orbit still changes shape over roughly 100,000 years, as it always has. Yet, for some reason, the climate system began following the longer cycle far more strongly than the shorter ones. Understanding why this happened requires looking at the climate system as a whole. not just at the orbital rhythms that initiate the cooling. The orbit provides the pacing, but the climate system decides how to respond. Something about that response changed around 1 million years ago. Ice sheets became more stable and capable of growing larger. Oceans began storing heat and carbon differently. Atmospheric patterns shifted. Feedback loops became stronger or more interconnected. These changes created a climate environment in which the longer orbital cycle became the dominant rhythm, pulling the planet into a deeper and more enduring freeze every 100,000 years. One idea for why this shift occurred focuses on the growing size of the ice sheets themselves. Before the transition, ice sheets were smaller and less stable. They grew and receded more easily in response to the 40,000-year tilt cycle. The tilt strongly influences northern hemisphere summer warmth. And during earlier climates, the ice sheets were shallow enough and sensitive enough that small changes in summer sunlight could melt them significantly. But as global temperatures slowly cooled over millions of years, ice sheets became larger. With each cycle, they left behind slightly more cold surface area. And over time, they built up a foundation capable of supporting thicker masses of ice. These thicker ice sheets behave differently from the smaller ones. Once an ice sheet becomes large enough, its height brings it into colder atmospheric layers. Its upper surfaces become extremely resistant to melting. Even if tilt-driven summer sunlight increases for a few thousand years, the ice may not melt as easily as it once did. This increased stability could have shifted the climate toward a regime where the shorter cycles no longer had enough influence to melt the ice sheet significantly. Instead, only the longest cycle, the eccentricity cycle, that modulates the strength of the tilt and precession effects, became strong enough to shift the climate between glacial and interglacial states. In this view, the climate system didn't start depending on eccentricity, because eccentricity became stronger. Rather, the climate system evolved into one where the 40,000-year cycle was no longer sufficient to produce large-scale melting. The tilt still varied, but the ice sheets had grown too tall, too extensive, and too stable to respond fully to the tilt cycle alone. It wasn't until multiple cycles lined up during periods of stronger summer sunlight that the ice sheets could retreat fully. These alignments occur roughly every 100,000 years. Another idea looks at the role of carbon dioxide. During earlier glacial cycles, the changes in carbon dioxide may have been smaller or more closely tied to the tilt cycle. But as the climate cooled slowly over millions of years, the ocean and biosphere may have begun responding differently. The deep ocean could have stored carbon in ways that made the climate more sensitive to long-term changes. If the ocean became more stratified, meaning its layers mixed less, it could hold more carbon for longer periods. This would make glacial periods colder and prolong them. The shift to a more stratified ocean might have reduced how quickly carbon dioxide returned to the atmosphere during the 40,000-year warm phases, preventing full interglacial conditions from developing until a stronger orbital alignment occurred. This idea suggests that as the deep ocean began behaving differently, the climate system became locked into longer cycles. Carbon dioxide became a stabilizing force that reinforced glacial conditions more strongly than before. Only when the eccentricity cycle lined up with strong tilt and precession phases did enough warming occur to release significant carbon dioxide from the ocean. This release would then support rapid warming, allowing ice sheets to melt and pushing the planet into a warm interglacial state. Without this alignment, the climate system could remain in a cold phase for longer durations. Changes in ocean circulation could also have contributed to the shift. Evidence suggests that during the million-year transition period, the patterns of deep water formation in the oceans changed. Deep water formation, especially in the North Atlantic and around Antarctica, determines how heat and carbon move through the ocean. If these patterns became more sluggish or shifted location, the ocean could store more cold water and more carbon dioxide for longer periods. This change would reinforce longer, deeper glacial periods. In this view, the oceans became a more powerful moderator of climate, slowing the transitions and lengthening the cycles. The shape and extent of land masses might have played a role as well. Continental drift is extremely slow, but even small changes in the connection between oceans or the rise of mountain ranges can influence climate over millions of years. A gradual uplift of terrain in key regions, such as the Northern Hemisphere, could have created new locations where ice sheets could expand and remain stable. The growth of large glaciers depends on altitude as well as latitude. If regions gradually rose over time due to tectonic processes, even by modest amounts, they could have become more favorable for the buildup of persistent ice. These shifts in topography might have contributed to the climate system's increasing sensitivity to long-term orbital changes rather than short-term ones. Another factor to consider involves dust. During glacial periods, large areas of land become exposed as sea levels drop, and ice sheets alter wind patterns. These exposed areas often become sources of dust. Dust affects climate in several ways. When it settles on snow and ice, it can cause slight melting by darkening the surface. But when present in the atmosphere, dust can reflect sunlight and reduce warming. Changes in dust levels could have influenced how efficiently snow and ice accumulated or melted. If dust levels became higher during certain periods of gradual cooling, the climate might have been pushed into a regime where snow persisted longer and ice expanded more easily. This could reinforce longer cycles of glaciation, especially when combined with changes in carbon dioxide and ocean circulation. These ideas do not compete with each other. They describe different parts of the same interconnected system. The shift to a 100,000-year cycle likely occurred because multiple components of the climate system reached thresholds around the same time. Ice sheets grew thicker. Oceans stored more carbon. Circulation patterns shifted. Dust levels changed. Vegetation retreated in ways that altered carbon storage and albedo patterns. Each change alone may not have produced a shift, but together they created a climate system more sensitive to long-duration orbital forcing. The concept of thresholds is central to understanding this transition. Climate systems do not respond smoothly to forcing. They can remain in one state for long periods and then shift rapidly when a threshold is crossed. Around 1 million years ago, Earth may have crossed such a threshold, entering a state where ice sheets were large enough and feedback loops strong enough to resist melting during 40,000-year warm phases. The system became locked into deeper, longer freezes that could only be reversed when the longer eccentricity cycle aligned with strong tilt and precession effects, reinforcing the summertime warmth just enough to overcome the ice sheet stability. Geological records provide evidence for this transition. Before the shift, the amplitude of the glacial cycles was smaller. Ice sheets grew and shrank more modestly. Carbon dioxide varied over shorter intervals. After the shift, ice sheets grew far larger. Sea levels fell more dramatically, and carbon dioxide levels reached lower glacial minimums. The climate swings became more pronounced. The cycles became longer. These observations support the idea that the climate system entered a new mode of behavior. Some researchers also propose that the cooling of deep oceans over millions of years brought Earth closer to a state of glacial instability. As the deep ocean cooled slowly, the entire climate system became more sensitive to small changes in sunlight distribution. When the pre-existing cooling trend reached a certain point, the climate system may have become more prone to longer glacial phases. This long-term cooling trend could have gradually weakened the influence of tilt-driven warming, making it harder for ice sheets to melt during the 40,000-year cycles. Only the stronger influence from the combined effects of several orbital cycles could produce sufficient warming to end a glacial period. During this transition, the shape and behavior of ice sheets themselves changed. Early glacial cycles produced smaller, more transient ice sheets that responded quickly to orbital forcing. After the transition, the ice sheets grew thicker and developed features such as high plateaus, deep valleys, and persistent cold conditions that made them more resistant to melting. These thicker ice sheets interacted differently with the atmosphere, creating stronger temperature gradients and altering wind patterns in ways that supported the persistence of ice. As ice sheets began to dominate the northern hemisphere landscape, their feedbacks became stronger, locking the climate into long-lasting cold phases. One of the most intriguing parts of this transition is how closely the new 100,000-year rhythm matches the eccentricity cycle. Even though eccentricity itself has a relatively small direct influence on the amount of sunlight Earth receives, its influence lies in how it modulates the effects of the tilt and precession cycles. During periods of high eccentricity, the differences between Earth's closest and farthest points from the Sun become larger. This amplifies the seasonal effects of precession and tilt. During periods of low eccentricity, these effects become weaker. If the climate system becomes dependent on strong forcing to exit a glacial period, then the eccentricity cycle naturally becomes the one that determines when a full deglaciation can occur. This view helps explain why the climate shifted into a pattern where only the strongest orbital alignments produced interglacial periods. The tilt cycle alone was no longer sufficient to melt the ice sheets fully. Precession alone was not sufficient. Only the combined effects of all three cycles amplified during high eccentricity periods could warm the northern hemisphere enough to melt ice sheets and produce the warm, stable climates between glacial periods. Another consideration is how greenhouse gas levels responded during the transition. Ice core records show that carbon dioxide levels during glacial periods became lower after the shift. Lower carbon dioxide makes the climate more sensitive to orbital changes because the greenhouse effect becomes weaker. If glacial periods reach colder baselines, then the climate system would require stronger orbital forcing to warm sufficiently for deglaciation. This would naturally favor the 100,000-year rhythm where the strongest orbital alignments occur. Even with these explanations, the transition remains an area of active research. Scientists continue to study sediment cores, ice cores, and geological formations to refine their understanding of how the climate system evolved. More recent models of Earth's climate suggest that the combined influence of ice sheet dynamics, carbon cycle changes, and ocean circulation shifts likely produce the transition. No single factor, acting alone, can explain the shift convincingly. Instead, the transition appears to be the result of the climate system becoming more tightly interconnected with feedback loops reaching new levels of influence. The shift to 100,000-year cycles also highlights an important aspect of Earth's climate: its sensitivity to long-term processes that operate on time scales far larger than human experience. The rhythms of ice ages are not driven by sudden events, but by gradual cumulative changes that eventually push the climate across thresholds. The million-year transition was not a sudden switch, but a slow evolution of the climate system toward a new mode of behavior. Understanding this shift helps clarify why the climate today behaves the way it does. We live in a world shaped by the long rhythms that resulted from this transition. The interglacial period we currently inhabit is part of the longer cycle that emerged after the shift. The pattern continues to influence the broad structure of Earth's climate, even though human activity has introduced new forces into the system. When Earth sinks deep into a glacial phase, it can feel, at least when viewed through geological records, as though the cold has settled in permanently. Ice sheets stretch across continents. Mountains vanish beneath moving ice. Sea levels drop, and the climate settles into a quiet, frigid stability that lasts thousands upon thousands of years. But this frozen state never lasts forever. Hidden within the cycles of orbital change are the seeds of eventual warmth. The same system that sends the planet into deep chill eventually guides it back out again. The thaw is slow, uneven, and filled with feedbacks that unfold across staggering spans of time. Understanding how ice ages end means understanding the delicate interplay between rising sunlight, shifting ice behavior, ocean adjustments, atmospheric changes, and the gradual release of heat and greenhouse gases that have been stored away during the long freeze. The beginning of the end of an ice age does not announce itself with any dramatic shift. It starts quietly as subtle changes in sunlight accumulate in high-latitude summers. Over many thousands of years, the tilt, precession, and orbit combine in new alignments. The orientation of Earth's axis shifts until northern hemisphere summers coincide with the part of the orbit when Earth is closer to the Sun. The tilt may increase modestly, sending sunlight more directly into polar regions. The orbit may stretch just enough to amplify these seasonal differences. None of these changes cause temperatures to rise immediately, but they slowly bring back slightly stronger summer warmth. The added sunlight begins to chip away at the stability that ice sheets have maintained for tens of thousands of years. Even as summers grow marginally warmer, the ice sheets remain massive and resilient. Their sheer size and elevation trap them in a cold climate of their own making. The upper surfaces sit in high, frigid air, where temperatures stay below freezing most of the year. This means early warming phases do not melt the ice wholesale. Instead, the first signs of change often appear along the lower edges of the ice sheets and in regions where they extend into lower elevations. These areas receive enough sunlight that when summers strengthen just slightly, melting becomes more effective. Meltwater begins to run across the ice surface, carving channels and exposing patches where snow no longer lingers year-round. The changes are small in the beginning, but they mark the first stages of the long retreat. During this early stage, the climate system remains delicately balanced. Snowfall may continue at high elevations, and cold winters persist, but summers begin to erode more than winters can rebuild. The ice sheets respond unevenly. Some regions may remain stable, or even advance slightly if local snowfall increases, while others thin and retreat slowly. The balance between accumulation and melting, held steady for tens of thousands of years, begins to tip. Once summers become warm enough on average to melt more snow than falls, the long downward slope of glacial ice begins. As summer sunlight strengthens further, the atmosphere responds in new ways. Air temperatures rise gradually, particularly during warm seasons. This warming reduces the persistence of snow patches that once lingered into late summer. Bare ground begins to reappear in areas where snow previously survived year-round. Dark surfaces absorb more heat than snow or ice, creating small pockets of amplified warming. These darker patches expand the following summer, allowing more energy to be absorbed and accelerating local melt. Once these pockets begin to spread along the edges of ice sheets, they create pathways where the ice can retreat more rapidly than before. The atmosphere's response to the growing warmth affects storm patterns as well. During deep glacial periods, cold, dry conditions dominate many regions. As temperatures rise, the atmosphere can hold more moisture. Storm tracks shift, bringing more precipitation to some regions and less to others. In many areas, warmer winters mean that more precipitation falls as rain instead of snow. This reduces the accumulation of snow that feeds ice sheets. In other regions, storms weaken because the temperature gradients that once drove strong wind patterns become less pronounced. The long, cold glacial climate begins to loosen its grip. One of the most significant changes during the end of an ice age occurs in the oceans. As the high latitude regions warm, sea ice begins to retreat. The retreat of sea ice exposes darker ocean water that absorbs more sunlight, warming the surface and allowing more heat to enter the atmosphere. This warming influences atmospheric circulation and helps reinforce the trend toward higher temperatures. Meanwhile, the deep ocean begins to adjust as well. For thousands of years, cold, dense water has been sinking to the ocean floor during the glacial phase. This deep water stores enormous amounts of carbon dioxide, which has accumulated through biological activity and limited mixing. As the planet warms, changes in wind patterns and ocean circulation begin to release some of this stored carbon dioxide. Warmer surface waters hold less dissolved gas, so they release carbon dioxide into the atmosphere. This release is gradual at first, but it accelerates as the oceans continue to warm. The return of carbon dioxide to the atmosphere strengthens the greenhouse effect, reinforcing the warming initiated by changes in sunlight. This feedback is crucial for pushing the climate into a new mode. Without the release of stored carbon dioxide, the warming might stall before reaching a full interglacial state. Vegetation responds to the changing climate as well. During glacial periods, cold temperatures force forests to retreat into smaller sheltered regions. Tundra and steppe landscapes dominate much of the northern hemisphere. As temperatures rise, forests begin to expand northward. Trees move into areas previously too cold for their growth. The expansion of forests changes the surface's ability to absorb heat. Forests absorb more sunlight than snow-covered ground or tundra. This contributes to further warming, helping to sustain the transition toward interglacial conditions. At the same time, melting ice sheets release meltwater into the oceans. This influx of fresh water can temporarily disrupt ocean circulation. In some periods, there is evidence that large pulses of meltwater slowed or altered the formation of dense sinking water in the North Atlantic. These disruptions may momentarily cool the climate or alter precipitation patterns, even during a warming phase. These temporary shifts do not halt the long-term warming, but they create a complex and uneven path toward the eventual end of the Ice Age. The climate system does not move smoothly toward warmth. It oscillates within the broader trend. As ice sheets continue to thin from the edges inward, large areas of exposed land begin to shape the local climate in new ways. Bare ground absorbs more heat, increasing local temperatures and accelerating melt. River systems adjust to the changing landscape. Meltwater floods low-lying regions and carves new channels through glacial deposits. Lakes form in depressions carved by ice. These lakes absorb sunlight and warm further, adding heat to the surrounding air during summer. The combination of exposed ground, expanding lakes, and warming atmosphere creates momentum that gradually overwhelms the stability the ice sheets once maintained. As temperatures rise and growing season lengths increase, vegetation expands not only northward, but also upward into areas once buried by cold, dense ice. This expansion alters the carbon cycle. Growing forests absorb carbon dioxide, but the warming oceans release more, and the release from the oceans dominates. Soil temperatures rise, accelerating decomposition of organic matter that have been locked beneath permafrost or left frozen for centuries. This decomposition releases more carbon dioxide and methane, contributing to additional warming. During the long thaw, sea level begins to rise as ice sheets melt. The rising sea floods coastal regions that had been dry land during the glacial period. Some coastlines retreat dozens of kilometers over thousands of years. Rising sea levels also reconnect ocean basins that were separated during lower sea level phases. This reconnection can re-establish major ocean currents that were restricted during glacial conditions. As these currents resume their interglacial pathways, they transport more heat toward the poles, accelerating the warming trend. In this way, the rising sea level becomes both a response to and a driver of the transition into a warm climate. The melting of the ice sheets changes Earth's surface in more direct ways as well. As the ice thins, the land beneath begins to rise slowly in a process called isostatic rebound. During glacial periods, the weight of the ice depresses the land by hundreds of meters in some regions. When the ice melts, the land rises gradually over thousands of years. This rise affects drainage patterns, river paths, and coastline shapes. It also influences regional climates by altering surface elevation. The rising land becomes less susceptible to flooding and begins to support new ecosystems. These changes contribute to the transformation of landscapes as the planet moves into an interglacial period. Deep within the ice, layers that formed at different stages of the glacial period begin to melt unevenly. Some melt water finds its way to the base of the ice sheets, lubricating the ground beneath them. This lubrication can accelerate the movement of ice, causing it to slide more rapidly toward lower elevations, where it melts faster. Faster ice flow can contribute to sudden retreats, where ice sheets lose significant mass in relatively short geological intervals. These rapid retreats do not occur everywhere, or at the same time, but they shape the final stages of glacial melting toward the later stages of the thaw. When the warming trend has become well established and ice sheets have retreated significantly, the climate system settles into a new balance. Summers become strong enough to prevent the return of persistent snow cover in most regions outside the highest elevations. Winters remain cold, but not cold enough to rebuild large ice sheets. Vegetation spreads across formerly glaciated landscapes. Rivers begin carving stable pathways that persist for thousands of years. Lakes left behind by the melting glaciers begin to shrink or drain as their outlets change. The climate stabilizes gradually into a warm interglacial state. In this interglacial state, the oceans resume their warmer circulation patterns. Carbon dioxide levels rise to new equilibrium values, warmer than during the glacial phase, but stable relative to seasonal changes. Vegetation reaches new geographic ranges. Ecosystems evolve to fit the warmer conditions. Coastal environments take shape along new shorelines. The planet settles into a climate that remains relatively consistent for thousands of years until orbital cycles once again shift sunlight distribution toward weaker summers in the high latitudes. The end of an ice age does not signal the end of the long rhythm itself. Instead, it marks the completion of one cycle and the beginning of another. Interglacial periods, like the one Earth currently inhabits, are temporary phases between longer freezes. The same forces that govern the retreat of ice sheets will eventually guide their return. As the climate moves through the continuing cycles of orbital alignment, the balance once again shifts toward cooling, and the slow descent toward another glacial period begins. Thinking about the future of Earth's long freeze cycles brings us into a space where geological certainty meets modern complexity. For millions of years, the rhythm has been steady enough that one could trace its patterns in ancient sediments, in the chemistry of ocean cores, and in the quiet layering of ice from ages long gone. Earth cooled, ice grew, sunlight weakened in northern summers, and the planet settled into its long winters. Then the cycle shifted, stretching from 40,000 years to 100,000. The ice thickened, retreated, thickened again, and each cycle left behind evidence of the forces that shaped it. Today we stand within one of the brief, warm interludes, living in a climate that would once have felt temporary, perched between the last great freeze and the next one. Understanding what the future holds requires stepping back far enough to see the entire pattern laid out. The climate system is enormous and slow, shaped by motions that unfold across tens of thousands of years. The orbit will continue changing its shape. The tilt will continue its steady oscillation. The axis will continue its long wobble. These processes are immune to human influence. They will persist long after current civilizations change or vanish. They are the baseline upon which ice ages have always been built. But the climate is not governed by orbital cycles alone. Earth responds to these cycles through ice sheets, ocean circulation, greenhouse gases, and other feedbacks that amplify or suppress small nudges in sunlight. This response can be altered by natural processes that unfold over millions of years, and by processes that unfold much more quickly. To understand whether Earth is approaching another ice age and when the next great freeze might begin, it helps to consider where we are in the orbital cycles. At this point in time, the variations in Earth's orbit are not aligned in a way that strongly suppresses northern hemisphere summer sunlight. The tilt is neither at its minimum nor heading toward its weakest state. The wobble currently positions Northern Hemisphere summer at the point in Earth's orbit farthest from the Sun, which favors slightly cooler summers. But the eccentricity, the shape of Earth's orbit, is relatively small. When eccentricity is small, the seasonal difference between Earth's closest and farthest distances from the Sun becomes minimal. This reduces the strength of precession's influence on climate. In other words, even though northern summers occur when Earth is farther from the Sun, the distance difference is not large enough to create extremely weak summers of the kind that typically start an ice age. If Earth were following only the orbital cycles and natural feedbacks that governed earlier eras, the long-term trend would still point toward another glacial period. The interglacial we live in, known as the Holocene, has lasted a little over 10,000 years. That is roughly the typical length of warm phases in the last million years, though some have lasted longer. If the orbital cycles alone were dictating the timeline, the next several thousand years would see a slow decline in Northern Hemisphere summer warmth. Snow might begin lingering through cooler summers at high latitudes. Ice might begin to accumulate gradually. The ocean would slowly adjust, and carbon dioxide levels would fall as the deep ocean cooled and absorbed more gas from the atmosphere. This slow shift would eventually lead to the first hints of ice age conditions. However, Earth today is not responding solely to orbital cycles. Human activity has changed the composition of the atmosphere at a pace far faster than anything seen in the geological record. Carbon dioxide levels have risen well beyond the typical range of recent interglacial periods. Over the past several 100,000 years, atmospheric carbon dioxide fluctuated between about 180 parts per million during glacial minima and about 280 to 300 parts per million during interglacials. Today, carbon dioxide levels are far above that range. These elevated levels influence the climate in ways that complicate the natural rhythm. Instead of preparing to cool, the climate has warmed. The oceans have absorbed large amounts of heat, delaying how quickly the climate might adjust to any reduction in sunlight from orbital changes. The presence of unusually high carbon dioxide levels in the atmosphere plays a significant role in determining whether the next ice age will begin on schedule. Carbon dioxide traps heat, reducing the capacity of weaker northern hemisphere sunlight to cool the planet enough for snow to accumulate year after year. The threshold for ice sheet formation becomes much harder to reach when greenhouse gases are abundant. Snow that might once have lingered through cooler summers now melts more readily. The feedback loops that support ice growth become suppressed. The climate's internal machinery does not respond in the same way. When the atmosphere warms beyond the conditions that typically precede glaciation, this does not mean that Earth has escaped the glacial cycles entirely. The orbital rhythms will continue to influence the climate. Over tens of thousands of years, the tilt will eventually reach phases where summers weaken substantially. Precession will alternate hemispheric summer intensities. Eccentricity will slowly grow, increasing the range between Earth's closest and farthest distances from the Sun. When eccentricity becomes larger, precession becomes more influential. Summers can become much weaker or much stronger depending on orbital alignments. These changes could eventually restore conditions closer to those that initiated the great ice ages of the past. But the question is not whether glacial periods will ever return. It is when. The climate system depends heavily on thresholds. Small differences can determine whether snow melts or persists. If greenhouse gas levels remain elevated for long periods, these thresholds shift. Instead of snow lingering through summer, it melts. Instead of the ocean cooling enough to pull carbon dioxide from the atmosphere, the warming ocean continues releasing it. Instead of vegetation retreating in ways that promote cooling, forests remain in high latitude regions where they absorb more heat than tundra or ice. The system becomes biased toward warmth. To understand how these changes affect the timing of the next ice age, researchers have modeled how the climate would respond to orbital cycles under different atmospheric conditions. These models suggest that with carbon dioxide levels above a certain threshold, the next glaciation could be delayed significantly. Some scenarios indicate that even if orbital cycles shift toward weaker summer sunlight, the warming influence of elevated greenhouse gases could prevent ice sheets from forming for tens of thousands of years beyond the expected timeline. In some cases, the delay could extend well beyond one complete orbital cycle, meaning the next opportunity for glaciation might occur much later than it otherwise would. This does not eliminate the long-term cycles. It simply stretches them. The orbit will continue shaping the potential for ice formation. But the planet might not cross the necessary threshold until conditions align in a way strong enough to override the additional warmth. If the climate remains warm enough throughout the next few precession and tilt cycles, then the earliest opportunities for ice sheet growth may be skipped. Earth has done this before, on smaller scales. Geological evidence suggests that during some warm, interglacial periods, particularly early in the Pleistocene, the planet skipped potential glaciations when sunlight patterns were unfavorable, or when the climate was too warm for snow to accumulate. Today, the added influence of elevated greenhouse gases could make skipping glaciations more likely. Beyond greenhouse gases, other aspects of modern climate change influence how the next ice age might unfold. Oceans store large amounts of heat. As they continue absorbing excess warmth, their ability to cool in response to orbital changes becomes reduced. This delays the cooling trend that normally precedes glacial conditions. Additionally, changes in ocean chemistry today will take thousands of years to dissipate. The deep ocean, which mixes on timescales of centuries to millennia, carries the legacy of current conditions far into the future. Even if atmospheric carbon dioxide levels eventually decline, whether through natural processes or long-term human changes, the ocean will release some stored heat slowly. This means the climate system may remain warmer than expected for thousands of years. The threshold for glaciation is not simply about atmospheric conditions at a single moment. It depends on how the ocean, the atmosphere, and the land surface interact across long spans of time. Another element shaping the future of the glacial cycle involves the geography of the planet. Ice sheets form more easily in certain regions than others. The northern hemisphere contains large land masses at high latitudes that favor the formation of persistent snow. But if warming changes these regions significantly, for example, by altering vegetation patterns, soil stability, or permafrost, then the early stages of ice sheet formation could be slowed or disrupted. The land beneath current and former ice sheet regions will also continue rising due to isostatic rebound. This rising land might create new conditions that either promote or inhibit future ice growth, depending on how elevations change relative to orally driven cooling trends. If we look beyond the next few tens of thousands of years, the orbital cycles will eventually shift toward a configuration that strongly favors a cooling climate. The tilt will decrease to lower angles that reduce summer sunlight. Precession will align northern hemisphere summer with the farthest point in Earth's orbit. Eccentricity will grow, amplifying this effect by increasing the distance differences. Under natural conditions, these orbital changes would be sufficient to start a new glacial period. The climate system would move slowly toward cooling. Snow would linger in high latitudes. Ice sheets would begin forming and expanding. The oceans would draw down carbon dioxide. The atmospheric cooling would reinforce the trend. However, the climate system that will exist at that time is not the same as the one that governed earlier cycles. It will contain the legacy of the modern era: altered carbon storage, modified ecosystems, warmer, deep oceans, and possibly human-altered landscapes. Even if atmospheric carbon dioxide eventually returns to pre-industrial levels, the slow response of deep ocean and ice sheet systems will leave long-lasting effects. Considering these long-term processes, it becomes clear that predicting the exact timing of the next ice age is not straightforward. The orbital cycles provide the structure, but the climate's response depends on a wide range of factors that evolve over time. If greenhouse gases remain elevated for extended periods, the next glaciation could be delayed tens of thousands of years. If future cooling processes, such as volcanic activity or changes in ocean circulation, offset some of the warming, the timeline could be different. The climate system contains many interacting parts, and their combined effects determine whether the threshold for glaciation is crossed. Even if the next glacial period is delayed far into the future, the underlying rhythm remains in place. The orbit will continue changing. The tilt will continue wobbling. The climate will eventually move into a configuration where ice sheets can grow once more. The long winter will return, even if it arrives later than expected. Earth's history shows that warm periods are temporary pauses in a deeper cycle. The interglacial we live in is not the end of the story. It is one chapter among many. In the distant future, when orbital conditions align strongly enough, the early stages of a new glacial period will begin with the same quiet persistence that marked earlier transitions. Snow will linger at high latitudes. Summers will weaken. Ice will begin to accumulate once humanity's influence has faded or been balanced by other forces. The climate system will resume a pattern that has shaped Earth for millions of years. It will do so gradually through slow adjustments in sunlight, snow, ice, oceans, and air. The long winter will return not with sudden force, but through a whisper of cooler summers, through slight shifts in ocean currents, through tiny changes in carbon cycling that accumulate across millennia. Eventually, ice sheets will thicken once more. Sea levels will fall. The planet will settle into its familiar deep freeze, repeating the cycle that has defined the last million years. And when that begins, the story of Earth's long rhythms will continue as it always has, quietly, steadily, shaped by forces that move too slowly for any single lifetime to notice, but powerful enough to sculpt the face of the world across ages.